Hi, everyone. Thanks for joining us today. So we're very excited to have, back by popular demand, another colloquium focused on the finite element methods for solving partial differential equations and their applications. We're joined today by a number of very knowledgeable speakers who have graciously accepted our invitation to speak today. So the format that we'll have today is that each speaker will present for about 15 minutes. During that time, the audience, please remember to ask questions in the Q&A panel. The speakers will be interacting with the audience throughout the event in the Q&A chat, separately from their structured presentations. So do ask any questions that you have. Since we have such a large number of very gracious speakers who have agreed to join us today, we might not have as much time for verbal Q&A as we have in some events. However, because this is a very popular topic, I can fully anticipate having more events like this. So do feel free to ask any questions that you have, because they might be the spark that leads us to say, oh, that would be a great follow-on session to have. So audience, thank you for joining us. Speakers, thank you also for joining us. Since we have such a packed, awesome schedule today, we'll jump right in. So our first speaker will be Oliver Rubin Koenig, who is the developer that leads most of our efforts here in FEM, or finite element method functionality. So I'll hand things over to Oliver, who will talk about what's new and what's coming up in Mathematica and the Wolfram language. And so thanks, Oliver, for joining us.
All right. Okay. All right, so you should be seeing my screen by now. My name is Oliver, and yes, I work on the PDE modeling and the finite element implementation, and I'm going to show you a bit about what we've been up to in the last few releases. So first things first, if you're new to this is probably the most important slide. So if you want to get an overview of what type of things we can solve with our PDE models, then the PDE models overview page is good. So if those are links, so if you click on them, the documentation will open up. And this is the reference page for the PDE models overview. And there you find a collection on different fields of physics that we've tackled. So you will find, for example, for heat transfer, you'll find the guide page here that has all the functions and boundary conditions that are related to it. There are a few monographs. There are PDE models that we have, and there's a section for overviews. How you can use these different PDE models. So if you have a specific boundary condition, I don't know, heat relation value, you'll see that's used in the buoyancy driven flow. So that's a bit of an idea of how this overview page works. The most important thing, though, is if your specific application is not on that page, that doesn't mean that we can't solve it. It just means that we haven't a pre-packaged PDE model for it. But that really doesn't mean you cannot solve it. You can use the low components of differential equation components directly and model your PDE. So that's not a hindrance. Okay. What I thought I'm going to be doing today is that I'm going to give a quick overview, since the last finite element colloquium that we had last year was beginning of the year. So this spans the releases 14.1 till 14.3. So the upcoming release, it's imminent in the next few weeks, I think. So we've made contribution or additions to these components: acoustics, mass transport, and heat transfer. There is new solid mechanics components. I'm going to show some of them. We have done a lot of work in electromagnetics in that period. There's some updates in fluid dynamics. We've updated the Schrödinger PD component. And I've also included some slides on the Open Cascade link, and I'm going to tell you a bit more about what that's about in a second. Okay. So in solid mechanics, we've introduced a new companion function, the von Mises stress function. I'm going to show an example in a second. We've extended plane stress and plane strain. So this is important if you do solid mechanics plane stress and you are interested in the Z component. So these are 2D operators. But if you are interested in the third dimension, the Z component, you can use the extended plane stress and plane strain components to do that. We've added new application examples. So here's one where we 3D print a mechanical design, and we use the finite element analysis to estimate probable failure points and things like that. So you can optimize your 3D print. And the last one that we've added here is a biomechanics example that uses a hyperelastic material model of a human tendon, and we show how various impacts on the tendon have an effect on how it behaves. So if you click on these links, the reference pages will open up, and you can then look at these examples in detail if you're interested in that. Okay, but getting back to the von Mises stress. So here's an example. So I have a fiber-reinforced hyperelastic material model. I have U and V are the displacement components. X and Y are the spatial components. Solid mechanics material model is a Neo-Hooken model. I have a reinforcement direction vector. So this material has some reinforcements in it and in this direction. A thickness of 1, a shear modulus, and a Lamé parameter. And this is the geometry. Now, when you want to solve something like that, you use ndsolve, specify the solid mechanics PD component with the variables and the parameters specified. You set a boundary load. So at x equals 1 at this right-hand side, we set a pressure in the positive x direction and a fixed condition on the left-hand side here to hold it in place. Now, then you compute the strain and the stress. You recover that from the displacement. And the stress is typically a 3x3 matrix with all these components. And that's a bit tricky to handle sometimes because you don't want to look at each of these components individually. So von Mises came up with a way to combine these stresses, these subcomponents of the stress tensor in a sensible way, the von Mises stress. And that is the new function that we've added. So you now specify von Mises stress, vars, pars, and the stresses you computed, and then you get the von Mises stress, which is an interpolating function, and you can then visualize that on the deformed to geometry, for example. Okay. Electromagnetics. So we started electromagnetics in version 14.0. We've added an overview in 14.1 and electric currents in 14.1. And in 14.2, we added magnetostatics for permanent magnets and quasi-static magnetic fields. So that was quite a bit of an effort to do that. And what's happening there is, so in electromagnetic, we solve, in essence, Maxwell's equations. However, Maxwell's equation, solving the full set of equations is complicated and resource intensive. So what you typically do is you try to find simplifications based on some sort of assumptions. And with these assumptions, you get to simplified models that you can use in specific scenarios. So here is an overview of the different components that you have. So if you are into electromagnetic modeling, the first question you ask, do I have a time-dependent system? Yes, no. And if it's not time-dependent, you know that the time derivative of the electric and the magnetic field are 0. Then you can decide, am I interested in the electric field or in the B field? If you're interested in the B field, you can decide whether you have a magnetostatic component, or if you have a magnetic PD component, so there you have an electric current. So this flowchart directs you to which PDE component you could use for different scenarios. Now, for the time-dependent case, you'll check whether the wavelength is larger than the object size. And if it's larger, then you're in a low frequency in a quasi-static regime. Then you can check again the skin depths and things like that. So all of these components are then available. What we are lacking, the last part that's lacking as a PD component, is an electromagnetic wave PD component. So this is the fully coupled Maxwell's equation. We don't have that yet as a component, but you can already do this on a lower level with specifying the PDE directly. Okay, so that's a bit of an overview there. So electric currents, we've had that in version 14.1. However, we didn't have the transient version of that. And the reason for that is that you have a divergence here and then a time derivative of the gradient of the potential. So this combination didn't work previously. And the reason was that the finite element parser just wasn't able to parse these type of equations. So what we've done for version 14.3, that's coming out in a few weeks, is the following. As a transition, we have, so you specify again the variables and parameters. You have the electric current PD component, and that gives you a PD component. So here's the divergence, and here is a time derivative of the gradient of the time derivative of the dependent variable. And you set up a geometry and the components. And the way to do this in version 14.3 is then to specify this option to say, use the new parser, and then it will do what it's supposed to do. It solves the problem. The reason that we have this with this obscure method option is changing the parser is quite a risky thing. If that goes wrong, then nothing will work. So we have to be really careful here. And using the new parser doesn't work in all cases yet. So we thought this is a reasonable compromise to allow this solving this specific equation, but not going to the new parser in full quite yet. Magnetostatics solves a magnetic vector potential. We have this in 1D, 2D, 2D axisymmetric 3D models, stationary models. So there is no current. So this is zero. If you want to model magnetic fields with currents, then you have to use a quasi-static magnetics setup where you can actually use an external current. So this is a vector valued equation, 2D axis symmetric models. You can also do 3D models with this, but in that case, setting up the boundary conditions can become quite complicated. So I've put it in braces here. We're thinking about maybe we can find a better approach to this, but you can do it, but you need to think a bit about how to set up the boundary conditions. The next thing that you're going to see also in 14.3 is that we've added axisymmetric fluid flow. So fluid dynamics was the last regime where we didn't have an axisymmetric version. So here we have a 2D geometry of two pipes that being stuck together and compressed a bit here maybe. And then you can now use fluid flow PD component. V is zero, so the rotational velocity component is zero. It's axisymmetric, and W is the fluid velocity in the positive Z direction, and the pressure. Specify a viscosity and the density. Region symmetry is axisymmetric, and then it generates the correct equations, and we set some boundary conditions to solve the PDE then. And here is a solution. So now I've taken this 2D solution and plotted in the 3D, in the rotational 3D object to give you an idea of what this then does. Okay. In physics, we've updated the Schrödinger PD component, and there we've added the possibility to model magnetic vector potentials in with non-isotropic effective mass. So this is a somewhat complicated approach, and you can model the Aharonov-Bohm effect with this. This is obviously something that's of interest for physicists, and I hope people find this useful. And there's an application example also for that. New application examples. So we've added an inductive heating example. So this couples magnetics with heat transfer. We have an electrostatic actuated MEMS. So this is, again, electric field with solid mechanics. In previous versions, we had a cerebral aneurysm, and in this version, we now also added, or in version 14.2, we've added a time-dependent cerebral aneurysm. So that computes the fluid flows through a cerebral aneurysm. Another addition there. Open Cascade Link. So in Open Cascade Link, we've tried to add 1D and 2D drafting. So this is a model of the surgical fixation plate. So this is in the forearm. This is a fixation plate. If it's broken, you can mount something into the forearm. And to generate this geometry, you can now use 2D primitives like splines, sine waves, and whatnot, and combine them together in 2D to make a 2D surface. And then you'll extrude that to 3D. So that this possibility is now available with Open Cascade Link. Open Cascade is basically the CAD engine that we can use to generate complicated 3D geometries. What's new in the FEM regime? So we've implemented fast time integration if one of the PDE coefficients is an interpolating function of a single variable, that is now much more efficient than it was before. MUMS is becoming a new method option for linear solve, and I get to that again in a minute. There's an updated function interpolation. I'm also going to show something about that in a second. And we have element mesh projection. So you can take a finite element mesh, a 2D mesh, and project it to 3D, or distort it and project it back to 2D, things like that. There is Neumann boundary unit normal. So that allows you to model normals in Neumann conditions, boundary normals in Neumann conditions. That helps, for example, with specifying forces in solid mechanics that are normal or non-normal and things like that. And I quickly already spoken about the parser update that's happening under the hood. Okay, for people that have ARM hardware, especially Mac ARM hardware, they had the problem that they had to switch to Rosetta to solve highly nonlinear finite element problems. And the reason is that on ARM, the Paradiso MKL Intel provided solver is not available. And for those, we now have added MUMS. MUMS is available on all platforms, also on Mac ARM without switching to Rosetta. For version 14.3, again, you'll have to specify this method option. PD solve object linear solve goes to MUMS. That's one option. And in version 15, so the version after the one that's coming out, this is going to disappear again. It's going to be fully automatic, but we're not quite there yet. So that's an update for these things. Function interpolation is a pretty old function, but we've extended that to be able to use any expression and evaluate that on a geometry on a region. And it's going to return an interpolating function that you can then plot. If you're familiar with evaluate on element mesh, this is now the system function that calls evaluate on element mesh to generate these interpolating functions. Okay. So just a few seconds about the future of PD modeling. So we're going to spend more time on making post-processing functions, equivalent strain, magnetic flux density, magnetic field intensity, fluid viscosity, things like that to recover from solutions. We're planning about spring and damper boundary conditions. We're working in solid mechanics on plastic deformation. And if you have something specific that you want to see, contact me. That's no problem. We'll see if we can fit it into the development schedule. Andy Solve rocks. Thank you. There's another 30 slides for which I didn't have time today. Those are more examples on things that I shared today. So I'm going to stop sharing and hand over to the next presenter.
Thanks, Oliver. So we've had some great questions already in the audience Q&A chat. So do remember you can feel free to use that as the presenters are going. It's a lot of exciting stuff that Oliver has been able to give us an overview of. So our next presenter is moderator of the Mathematica Stack Exchange. You might know them as X, and so I'll hand the presentation over to X.
X, I think you have your mic off. Could you please turn it off on?
Oh, okay. Can you hear me?
Yes, we can hear you now. Thank you.
Okay. Okay, let me start. Okay. Let me share something today. It's 8 a.m. here. Hopefully the neighbors will come and notice that. Okay. Okay, let me start. Well, then we all know that NDSOL is a powerful tool for solving PDEs, but there exists quite a number of PDEs, including some well-known prevalent that cannot be handled by any software. For example, those PDEs include integral, those specially first order PDE, or PDE, programming algebraic equations, and fractional order PDE, and the DIL focus on this shockwave. And let's see a simple example. This is from one post in Stack Kitchens at showing Borders equation with initial at the last time. This is a seemingly simple system, but if we show it with initial directly, we will see the solution runs quick very fast. One may naively think that if we use a denser grid, perhaps the solution will be improved, but it's not true. Here we use 2,250 coins to solve the problem, but we see it get worse. So why does it fail? It's because the PD has a special term here, and essentially the PDE, the solution, is no longer a solution in traditional sense. It's not smooth. It's not smooth at this point, and it can no longer be described by PDE in the classical sense. One possible way to handle this problem is to add the artificial viscosity, but its vanity. You see, we need to adjust the grid to resize in a very tricky way. Use a very dense grid and set a high enough difference order, then we can obtain this. But this solution is very unstable because, let's say, for example, we tend to second order difference grid. And you see, head warning shows up, and now it's fine, but it's no longer precise solution. So back to the 2022, the user Noah has introduced this article in his answer, and I'm quite impressive because the algorithm in this paper is relatively easy to understand for average user like me. And so I decided I should implement this package, this algorithm in a general way. As a general, so it's 2022. And then actually, shortly after posting this comment, I managed to finish the prototype of this package, but it's just too hard to use, so I don't release it. By this time, after I received the invitation of this talk, I decided I should finish it and make it public, and finally I made it. The packaging can be used to show this type of PDEs. Let's see the example. I think it's a bit complicated, but you are not using it. So let's see example. Let's go to example. Okay, let's first consider the classical example. Solid cube here. This is also from one post in Stack Exchange. This is classical IPVP for the Jurassic twin in one dimension. And you can see the syntax of this page is very good in direct. Here, the U list stands for the matrix in the time derivative, and the F list stands for this matrix. And after setting, then the show with 7 arguments will be set out in this data. Yes, you will no longer need to set a non-zero number for the 0. And let's see the output. Quite nice, right? Here, we need to adjust the accuracy goal and the precision goal a bit. You see, usually the default setting is higher than this. If I remember it correct, it shall be 4 or 5 or 6. Let's see. Next example. Okay, this is the one example in the original paper. One may think that this PDE can be handled by an initial directory, but as you can see, this epsilon is very small, so an initial will have difficulty with it. And as you can see here, at second order thing, and in the standard form of this PDE, there's no role for it. It is introduced in the source here. So in the package, I have introduced 3 functions to handle the derivative thing. They are FW, BW, and CT, which stands for forward, backward, and center. So you can see the line strategy. Then now we can see this solution is relatively nice. Of course, we can turn off the epsilon. Sorry. You can see the solution becomes sharper compared to the one with non-zero epsilon. And with another example from the paper. And somewhat similar to the previous one, but this one is more challenging. and we have to adjust the option of the package, the theta option is loop. Though the theta value is explained in the original field, but honestly speaking, I couldn't understand the explanation in the original field very well. Stepping job, but after some testing, I noticed that the difference of its theta value is very obvious in most cases, but larger theta results in a slightly sharper solution. And in this example, we need to lower it a bit, set it to 1, and obtain this. If we don't set the theta value to 1, let's see what will happen. Oh. You can see the difference. Okay, let's see the example at the beginning of this talk. It's the one-dimensional bug situation with periodic boundary condition. You can see that in previous examples, I haven't explicitly set the boundary condition because at the default setting is 0 Neumann condition. But in this case, we need the periodic, so a function periodic has been built in this package, and we need to call it in instead. So the function this function to periodic, and again the syntax is very straightforward. And notice that I finally decided to allow a flexible syntax for hypersolver, so you can mix each of function value and the function relationship is allowed in this package. You can see here I use a function relationship with the independent variables, but in the previous example, they're not there. You see, the T and X is not there. And here's the output. Let's see some further examples. Here's a Euler equation in 2 dimensions. Cylindrical explosion. You can see Mr. no longer fits the description in the paper, because in the original paper, the shortcut is limited to entering in this form. And again, honestly speaking, I can't understand the original explanation very well. But again, the medical test suggests the Q10 can be quite general. You can see, listen, we directly correlate the mathematical and see the effect. Here's the most advanced part of this code. You see, we need to set U to be 0 at 0. So we need a customized BG font. This is a bit advanced and only the counting out by railway to make the similar, but as you can see, this is the output. Let's compare it to the result in the textbook. You can see they agree well. And as a verification, let's show it in two-dimensional Cartesian coordinates, and you can see the result is almost the same, but you can see some very small difference. So perhaps I haven't finished for the tests for the source 10. Okay. Final example. You're using 3D spatial explosion. This example is somewhat similar to the previous one, but here I just want to show that this technique is in principle. In principle, we can handle n-dimensional problem with this package. But of course, for high-dimensional problem, for example, here we are showing a 3D problem. It becomes very demanding. We need almost an hour to handle it in three-dimensional problem as a three-dimensional problem. And the result, because we are using only 100 point, you can see it's not as sharp as the essentially one-dimensional. So it's compared. You can see some small discrimination. And okay. I think you will already noticed it. This package is still not general enough, and since it's a FDN implementation, irregular domain cannot be handled by the package. And of course, variable coefficients cannot be handled too. And it's not quite easy to use those that maybe once come across my PDE 2D and PDE training, that we have noticed that so many years very little people manage to understand the usage of PDE 2D, and I'm afraid the hypersolver, well, it's harder to use than PDE 2D and the PDE 2D, and we know that at least since 2007, we can find the following paragraph in the document of mathematics. You can see that in this document page, the yellow schemes and for example, the forward difference linear branch checking. These are all classical algorithms that can be used to handle the shockwave. But so many years pass, and they so it's still not building. But who knows? Fast they'll be implemented in next watch. Okay. That's all. Now let's make the package.
Thank you so much for the contribution to the Colloquium. We had some audio issues from the microphone, which unfortunately I don't think any of us can fix because of people connecting all over the world for this Colloquium, which is fantastic. But audience, if you had any particular questions for the speaker that you couldn't quite hear the microphone, you do feel free to let those know, and we'll be sure that we can communicate through chat and, of course, Mathematica Stack Exchange. But we did have some audio issues with the microphone lagging a bit. But thank you so much. Okay, so our next speaker will be Safi Ahmed, who will be talking to us about his work in modeling PDEs. And without further ado, I'll hand it over to Safi.
Thanks, John. Let me share my screen. All right, can you see?
The audience can see, yes.
All right, cool. So, greetings, everyone. I will be talking about switching physics by region. So, what that means is that what do you do when different part of your system need different partial differential equations? So, for instance, here you see a flow channel that has a free flow region as well as a porous region. And such kind of examples you can see in, let's say, water filtration systems, where water tends to flow through different types of regions, such as a free flow region and the various porous regions where the filtration takes place. And the flow of water in each of these regions is governed by a different set of differential equations. So how do we model such a system in a very elegant and modular way? I'll be talking about that. My name is Safi Ahmed, and I am incoming assistant professor of mechanical engineering at the National University of Science and Technology in Pakistan. And I also had the opportunity to attend the Wolfram Summer School 2024, where I developed various fluid flow algorithms in Wolfram Language. All right. So the problem with a lot of PDE modeling problems is that these systems don't follow the same physics everywhere, or the same PDEs everywhere. So as we saw this channel also in the previous slide, you have a free flow region that is governed by the Navier-Stokes differential equation, and you have a porous region that is governed by the Brinkman partial differential equation. Also, similarly, you have examples like this from all over the place. So, for instance, this is a fuel filter system, and here you see that fuel passes through this filter system through a valve, and here you have a porous region inside the filter system, and there a Darcy equation applies, and in the free flow region, Navier-Stokes equation applies. Similarly, heat flow through an automotive radiator. You have the free flow region, and you have the conduction going on in the solid plates, where you have the Fourier's law of conduction. And in the free flow region, you have the convection diffusion equation. Similarly, also in human body, let's say take human liver, which has all sorts of enzymes going in and out of it, into and out of the bloodstream, and this is called interstitial flow. So this kind of examples you can also find in human liver, where you have different physics or different PDEs governing the different equations, governing the different regions of the system. So the thing here is that NDSolve is great. You can see on the left, it solves very beautifully differential equations. However, the where it gets tricky is that when you have different PDEs being applied at different regions within the same system. And so here you have on the left hand side, you can see a very elegant solution. And on the right hand side, what you see is this huge amount of code that is needed to solve this equation and to get to the solution. And you have in this code, in this messy code, you have the if statements flying everywhere. The boundary conditions get complicated. And so the point here is that things get messy really fast when your model needs more than one PDE, or there are different PDEs governing different regions of your system. So what if you could model smarter and not harder? So one concept that we have within Mathematica is the concept of region marker. So basically, what you do in this in implementing the region marker approach is that you assign indices to different regions within your system, and that way you can assign different PDEs to to those various different parts of the system. This is explained on here on the left hand side. As you can see, if the region marker is 1, use Navier-Stokes PDE. If the region marker is 2, use the Brinkman PDE. All right, but what I did in this recent project is that I had, so there's a fluid flow PDE component in Mathematica, and so what I did is that I created my own Brinkman PDE component to model the flow within the porous region, and then I had this modular PDE structure, or a code that was very modular. So to say a bit about the PDE components, Wolfram Language has these pre-built PDE components like the fluid flow PDE component and the heat transfer PDE component, which give you the terms of the differential equation of the respective physics that you are trying to solve. And if a PDE component related to your problem does not exist in Wolfram Language, that does not mean that your problem cannot be modeled using the Wolfram Language. And what you can do in that case is that you can, of course, explicitly write down your PDE model, or you can instead define a custom PDE component that makes your code more modular. So again, you see you have a built-in components, and they can be combined with the custom components to give you a very modular structure of your code when you are modeling problems where different physics apply to different regions in your model. And so this modularity allows for a very elegant modeling of a complex system, such as the Navier-Stokes PDE for free flow and the Brinkman PDE for the porous flow that we just saw earlier. And this also makes your code more scalable to further problems, or if you want to facilitate the reuse of your equations or your code for various different problems, whatever you're working on. So this modeling strategy applies in examples across domains, as we saw earlier. And in each of these examples, you have different regions that obey different physics, and the challenge is basically the same. And how do we model? How do we create a model in a way that is very that is modular, elegant, and very adaptable to the different problems that we need to solve? All right. So when I started studying this concept, I had this code to start with, and basically we had no PDE we weren't using any PDE components, and we were just using writing the PDEs explicitly. And here you see the model where we have written the PDEs for the Navier-Stokes and the Brinkman equations in very explicit form. And you see that it's a rather messy code where you have like lots of if statements. And yes, it does give a solution. But what we see here is that this code is somewhat not scalable. If you want to, let's say, solve a different problem, or you want to go from the simple geometry to a bit complicated geometry, this kind of code is hard to scale. And so you note here that the region marker is used to switch physics that we will make use of, and the model works, but the code is not modular. And so I realized that if I want to reuse and share and extend this PDE model, this model will not scale well. So what can we do in that case? Well, enter fluid flow PDE component. There's a PDE component in the Wolfram Language, built-in component that allows you to model fluid flow. And so when we implement the fluid flow PDE component in our geometry to model the free flow, what you see is that you go from this messy code on the left to a very compact and a very modular code on the right, where you simply have a fluid flow PDE component, and the dynamic viscosity and mass density very beautifully go inside that component. and it gives you the same solution. All right, same physics, but very cleaner and very ready to scale. And so, all right, so the one of the benefits for using this modular code is not only that your code becomes more elegant, but it is also optimized for speed and stability, because the expert teams at Wolfram, they optimize these functions for the for speed and stability, and so that becomes rarely a concern when we use these modular functions, especially the built-in functions. All right. So now we had Navier-Stokes equations being modeled through the fluid flow PDE component. Now, I also wanted to make my code modular further, and so what I did is that I wrote my own component called the Brinkman PDE component for the porous region. And what you see is a screenshot of the documentation, which you can find in the material as well, and you can play with it. You can use it for your own applications as well. All right. So what we get here when we combine the fluid flow PDE component, which is the built-in function, along with the Brinkman PDE component, which we custom built, we of course get a modular and more elegant code. And what you see here is that we went from explicitly writing the PDEs to using the fluid flow PDE component, which made the code more modular, but there was no explicit, let's say, module for porous flow. And so when we introduce the Brinkman PDE component, now you see that we have in our code, it is very elegant. We have the fluid flow PDE component, you have the Brinkman PDE component, and the various parameters such as porosity, permeability, dynamic viscosity, they all beautifully go into this code. And this code that you see here is also provided in the material. All right, so this pattern, it gives you a solution, and it not only works, but it also travels to various different examples. And one thing that we need to note here is that there are certain numerical inconsistencies that you see in the solution here. And these are due to maybe due to the structural differences between the built-in component and the custom component that we built. However, the solution is stable and it converges well and it remains insightful for the practical purpose. And this pattern can be extended to more to other examples. These are some exciting directions. We saw them earlier, and we can try and use these components for these further examples. All right. So what we have, so we have provided some material that you can download. And from the materials, or at the end of this presentation, you can find a link, and you can play with the Brinkman PDE component and also the coupled flow model that you can see here on the right, and you can play with it and try to see how this modularity can be implemented when modeling PDEs, when you have different PDEs being implemented in different regions. All right, and you can use these provided material to as a learning tool to create your own models. If you, let's say, if you are in the heat exchanger space, or you are even in tissue scaffolds, you have different PDEs governing the different regions in that tissue scaffold. All right. So this is a modeling pattern that scales with the amount of people that you have in your organization. So for instance, if you have like a single researcher working on these models, if the code is modular, then it can be better shared with the other team members, and similarly with your engineering group or your lab. Or so the point here is that this modeling logic becomes an asset and not just limited to only single person. And if a team member leaves, or if a graduate student leaves, they don't walk out with this model. Other people in your team can understand if you have modeled your PDEs in a modular and scalable way. And if you are, let's say, if you are hiring a new person, then you can onboard them on a working simulation in days and not weeks. And this clean modularity means less time debugging and more time discovering new solutions. All right. So I would love to hear like what you are working on, and if this talk has sparked something in you, I would love to hear about it. And you can find the materials in the materials section or on this website. Thank you for being here. I am happy to keep the conversation going.
Thanks very much, Safi. We really appreciate your presentation. So our next presenter will be Jurne Slanovic, who will be presenting on topics relevant to PDE modeling and his work. So I'll turn it over to Jurne as soon as we have.
Okay. Please let me know if you see the screen that I'm sharing.
The audience can see the screen, yes. There is still the slide side view, if that's, there we go.
Good. So welcome. My name is Jurne Slanovic, and today I will be talking about how we use Wolfram Mathematica to solve heat transfer problems, specifically when it comes to development of heated radomes. Now, before I begin, I must introduce a bit my company and myself. So I come from Hela Saturnus, Slovenia. We are located in Europe, and our company is basically a subsidiary of Hela Group, a global company. And Hela Group, together with Faurecia, forms a bigger entity, Forvia. So this is just for the context why the logos on the slides are such as they are. Now, what we do in our company, we develop and manufacture lighting equipment for automotive industry. And basically from start to end. And my role in the company is that I'm the simulations manager. We do various kinds of virtual simulations in our department. And why we do this? Yeah, to support and guide the development teams to reach good concepts early and right first time. Okay, so let's get started. The speak is, or the talk is divided into, let's say, 5 sections. First, I will make a short introduction, then I will highlight the problem. Then I will spend a bit more minutes, a bit more time on the cool tool. A cool tool is basically the Packlet that I have developed and is helping us to tackle these problems. Then I will switch to live demo in Mathematica and then some concluding ideas. Now, because the timing is rather short today, I will be moving along the slides rather quickly, but I think that you will get the main idea. Okay, so to get started, maybe just what the radome is. A radome is basically a protective structure around the radar sensor. Typically, if you look, for example, on the airports, this structure has a shape of a dome. Hence, the term radome is used. Yeah, radar plus dome is radome. But also on the cars, in automotive industry, we use the same term, although typically the radome on a car doesn't look anything like a dome. Typically on the car, we are faced with radar sensors on front of the car. And you can imagine these sensors then detect the vehicles in front of you, keep distance, and for safety reasons is basically why they are used. Yeah, 2 words about functionality. Twofold functionality, one could say, is the radome. It must look nice, and it must be as transparent for the radar waves as possible. And especially this transparency when it comes to, let's say, harsh conditions, wet and cold, is in danger. Why? Because ice might form, we don't want this, or ice might be already present and we want to de-ice it. And for this reason, a lot of the radomes that are developed nowadays are heated. And our motivation was to develop a tool in Wolfram Mathematica that would give us a flexibility and like a fast response time to, let's say, answer to development teams like what if we make this modification, what if we change the material, and stuff like this. So this was our aim. So going further, what the problem is on the left side of the slide, just a couple of paragraphs about the problematic. Basically, the thing is that radome must be a dielectric to transmit, to be transparent for the radar waves. So typically it is a plastic. Plastic is a poor conductor. And what this means is that because the heating is typically realized by so-called heating wires, which are embedded deep or inside of the radome and then energized with electric current, this heat is at risk of either not getting to the front surface well enough, so you might get ice, or if you energize the wires too much, you might trap too much heat near the heating wires and you might damage the radome material. So this is the main reason why we wanted to develop a tool that would give us more insights into what's going on. How we set up our reasoning, we simplified the actual radome, approximated it by a rectangular cuboid. Then we took a 2D plane, made a slice over this simplified geometry, and what we're left with is this 2D model, which just by looking at it is really nicely suited for further analysis in the Wolfram Mathematica. Now, going to maybe more numerical formulation of the problem, what we are then left with is we want to solve the heat transfer equation on this 2D domain. And how we do this is we use the finite element method in Wolfram Mathematica. For this, I think it is general known, we must understand and provide proper boundary conditions, then heat sources. And our aim when setting up to develop this cool tool was that we wanted to model multi-layer structures, also with air gaps, with ice layers, meaning that we needed to include nonlinear, that is temperature-dependent material properties. Okay, now cool tool. This is a packlet. Unfortunately, it is not publicly available. It is used by our department. On this slide, I'm just showing, let's say, three things or three features or three main steps that build up this cool tool, meshing. So what we do is we use element markers to elegantly control the material properties of different layers or mesh sizes. Then when it comes to solving, we use the built-in heat transfer PD component. And this is really, it was mentioned in the previous talk already. Before we were using this, we were manually setting up equations. And this was like a day and night difference compared to what this offers you. Because the system of equations is really handled and defined elegantly. Then when we have the system of PDEs, we use ND-solve or parametric ND-solve to solve the problem at hand. One other thing that I would like to mention, it has more to do with user friendability, pre and post processing, Basically, how such a system is defined is through associations. So we have key value pairs, for example, and these key value pairs then determine the properties of the layers, the geometry of the layers of the wires, and so on. To make it easier for users to use this tool, however, we have built a user interface called Model Builder, and I will show this in a bit later on. Post-processing, the main results that we get from the NDSolve or parametric NDSolve are temperature and heat flux distributions in this 2D domain. And based on those two main results, we derive many other useful functions that are suited for our needs. Okay, so the key capabilities. I will maybe go over this slide not in detail because I would really like to spend a bit more time in the live demo. But what I would like to emphasize is this operational range functionality. Basically, this was also one of the key questions that led us to develop this tool. We were constantly asking ourselves, what is the optimal power to reach, for example, front surface temperature, I don't know, 20 degrees Celsius, or how much power are we allowed to provide to the radome not to melt it? So this was, I would say, the key question that led us or motivated us from the start. And then these two, Model Builder and interactive simulation, simulator dashboard, these have more to do with user friendliness, but still we think this helps us to be faster, especially when using this tool live in meetings, for example. And the documentation, I should say that there are, let's say, over 100 function pages already assigned to this Packlet, and the technical notes are also growing each month. And why I'm mentioning this is because when one is building the code and then you decide to go, okay, now I need some documentation, often you find yourself maybe not knowing as much about the phenomena as you think that you knew about it. Yeah. So when you try to write documentation in a manner so that it is understandable, you often make some retrospective into yourself and see, oops, this is not like I thought it is. And the other thing is that you also see that maybe naming was not optimal and you do certain iterations. So that is why I'm mentioning that documentation helps also to improve the code. Okay, so now I will switch to the Wolfram Mathematica notebook. It is not a presenter notebook, but I hope it will be possible to follow. So model definition, I mentioned. The stuff that is basically defining our model is an association. So we have some key value pairs. For example, which kind of simulation type are we talking about? Then some data about the wires and stuff like this. But this, of course, is simple and easy to use by a skilled user. But to make it really more easy for a general user to use, we have built this so-called model builder. And here one can, for example, select which kind of simulation one would like to solve. There are quite a few steady state or transient simulations available. And if I click and choose one simulation type, it offers me this GUI, which basically just guides you and prompts you to input the material properties, the geometrical properties, whether you have single, multiple wires. So really an easy way how to define the model. And then you simply here, you give it a name and click generate model, and that's it. Here, for example, I have a few models predefined for this webinar. And if I just show you, For example, now I have in this demo model database, I have loaded 3 models, 1 layer, 3 layers with finer mesh and with ice. Maybe if I click, this one, what I would highlight here is maybe that you see this thermal conductivity definition. It is a function air thermal conductivity, which depends on the variable T. Why this is neat? The code is written in such a way that as soon as material properties are a function of a variable T, the code then assigns this variable T to the dependent variable in the code, and it handles it as a nonlinear material property. Simulation settings, I won't go into all the details what we can choose, but maybe meshing, automatic, manual. Here we have automatic mesh. For manual mesh, one can easily just say, okay, wire mesh is in this case 0.02 millimeters for the wire. And the layers, because to be honest, the geometry is rather simple, we use such a list which then determines the element size in each of the layers. Solving is done simply by calling the function simulate. The function simulate will know which function to choose because the correct type of the simulation is a part of the model itself. Yeah. So the sim type key points to the value, which then determines which simulation to run. So let's just an example. In case of a parametric solution, we get this parametric function as a result, and we see in this case this was a steady state simulation. We have dependent variable, this is the temperature, and then spatial variables. And why these parametric functions are really useful for our purposes is that it is a really convenient way for us then to provide this solution with parameters, for example, power, front and back, ambient temperatures, heat transfer front back, and then you get the actual interpolating functions that are the solutions that you want. So this one is the temperature, and this is the gradient of the temperature. However, we rather work with then higher level functions, so we don't work directly with the solution, but we, for example, define temperature. And what we do here is we simply provide the arguments of the model, then the boundary and load conditions and the 2 spatial variables, and you get a neatly meaning. I mean, it is a more intuitive way of using it. Yeah, and same for the heat flux. Building on top, I'm just showing you how we were building up the Packlet. So also functions like this, often, whenever we use this tool, we're interested in the temperature distributions. So without or not to constantly call and write control plot and provide all the arguments, there are simply functions that do all this instead of you. So it is nothing fancy, but just for ease of use, this is defined. Okay, I will speed up. Interactive dashboard. This is something that we are using really efficiently during live meetings. What we do is we call the function radome heating simulator, provide the model. This is basically a dynamic object, a combination of manipulate and some dynamic commands. On the left side, we have the input data, the environmental conditions, and on the right-hand side, we have the results. Here, I would say we have defined or coded the most relevant stuff. So, for example, we can easily see how the temperature changes with velocity, or we can see, for example, the streamlines of the heat flux, which it might not be that relevant to you guys right now. But when we are looking at pictures like this, and then maybe change the velocity, ambient temperature, front, back, rerun the simulation, one gets an idea how efficient the system cooling or heating is. Yeah, and then maybe one function that is really neat is this operational range. So because in this case we are using the parametric ND-solve, we get the solution nicely provided. Now it has, hopefully it will not break down. So we just say, okay, please calculate for me at different velocities how much power we are allowed to put into the system, what is the power that we must provide to the system so that the front surface is at desired temperature, and you get curves that are easily to understand and also to discuss with the colleagues in your teams. Yeah. So it seems that now something has started to jam, but if it will not correct itself, I will just go to presentation, because mainly what I wanted to show is that by using this process of, or this availability in Wolfram Mathematica, the discussions or analysis are really efficiently communicated within the team. Yeah. And anyhow, I think I'm getting to the end of my time slot. So to conclude, what I would like to maybe highlight is this easy to combine different tools within Mathematica. Okay, why we build the cool tool is to complement our existing full CFD software with something that is fast and still easy to use. And maybe one thing, and then I will be over, by having this tool available, I have noticed that the communication with my team was becoming really fruitful. So the benefit of this tool is maybe not only in the results that it gives you, but it really fostered the brainstorming, the innovative thinking among the CFD team members. And this is the unexpected benefit of having this tool. And last, this documentation. When I was writing this code, I still am writing the Packlet. Really, it is from week to week. I rename stuff. I make it a bit more clearer, and so it also teaches you as a code developer each week something new. So with this, I would like to conclude, and hopefully I was not too much over the time.
Not at all. Thank you, Jurnay. I believe we do have some audience questions showing up for you in the Q&A now. So if you could please take a look at that as we transfer to our next presenter. Thanks so much. Okay, so our next presenter will be John Dunlap, who works on biological physics at University of Salzburg, Austria. So I'll hand things over to John.
G'day, everyone. Hopefully you can hear me. I'll just share my screen. Hang on. And we should, hopefully you can see my slides. Can you hear me and see my slides?
Looks good.
Great. Well, once again, thank you very much for the invitation to present some of our work here. I'm going to be talking mainly, I guess, on the application side, in the sense that I want to show how we can use inbuilt functions in Mathematica to actually solve biomechanics problems. And of course, in biophysics, biomechanics, in a lot of our research, a lot of this stuff is not done alone, although I do quite a bit of coding in Mathematica by myself. I work a lot with experimentalists, in particular, a very good collaboration partner, Michael Eder, Peter Fratzel, and others that are named here. But you'll be able to see in the publications who are the other collaboration partners. So the thing that we're interested in is that plants, although they seem fairly static, they can move. And there's one example that probably many people will know, and that's the pine cone we can see here on the left-hand side. And this responds to the stimulus of drying and opens up, allowing the seeds to be released. There are other examples, for example, on the right-hand side, where it opens when it gets wet. So this is an ice plant. You find them all around the world in sort of dry coastal areas. And the seeds are then released and splashed out with rain. So this is all pretty interesting. And there's been quite a lot of work that's been done trying to model and understand this sort of process. But it turns out there are other systems, and if you can tell from my accent, I'm not Austrian, I'm Australian, and there are systems where they respond not only to moisture, but also to fire. So you've probably seen many images of bushfires in Australia, and many plants have adapted over evolution to respond to the signal of fire and use this for advantages. So here's an example of a landscape after fire where we can see a lot of dead trees, dead and burnt trees, and in the undergrowth here you can see the new plants coming back. You can also see some of the reasons why this occurs in these images here, where you see these seed capsules, and you see these unburnt regions where the seeds have been released after the fire has gone by, meaning that you have a mechanism that responds to fire, releases the seeds, not during the fire, but when the fire has actually passed and there's sufficient moisture available to germinate, sufficient nutrients, and no more competitors. So these sorts of fire adaptations are not only found in Australia, but you find them quite often in Mediterranean climates. For example, in California, you see them also in South America, South Africa, and of course the Mediterranean, highlighted here in green. Now in Australia, there's a genus of plants that specifically respond to fire, and these are called Banksia. And there's about 170 species, including a special group called Dryandra, which is slightly debated. And there's many different sizes, shapes, and different styles of response to climate, as you can see in some of these different images here that you find from the region of Western Australia. And so one of the things that we're interested in, and my colleagues are interested in, is to understand what is the role of material properties, geometry, in the ability of a plant to hold seeds inside a capsule, wait for the particular signal to come, be it fire or water, and then give rise to some sort of response, allowing the seeds to be released. Now, how do we go about doing that? Well, one way you can do this is you can take such a capsule containing many seeds in there. So we have these follicles here that you can see in this video. And then when you set it on fire, you can see one of these capsules here embedded in the fruit starts opening, only partially opening, so the seeds are still protected. But then when it's further wettened, equivalent in nature would be when after a fire, if it rains afterwards, then you get the full opening and then the seed is released. And so what we're trying to do is to see how we can model this sort of behavior in order to see the role of geometry and material properties. And there's some interesting things that were found out by a colleague of ours, Jessica Huss, where she took samples from the same species across a climatic gradient, and she discovered that those in the north, that is in the hot regions, open at higher temperatures than those in the south that open at lower temperatures. And what we think that this is due not to genetics, but it's due to geometry, which is somehow a response to the local environment. Now, how do we go about doing research on this and using Mathematica? I'm giving more of a scientific presentation here, but it maybe gives you an idea of what you can do with the ND solve capabilities in the finite element method. So the experimental data that we were dealing with is we took 3 species of Banksia. We put thermocouples in the back of these seed capsules. We hit them with a Bunsen burner, so we had a thermal couple at the front and at the back, and we could measure temperature profiles as a function of time, and we could get an idea of how heat was transferred through the material. Furthermore, we could measure thermal properties, and then we used the built-in functionality of Mathematica. So we took 2-dimensional slices of 3-dimensional structures. We segmented these and then produced a mesh, and then we could model, for example, heat transfer. We applied a heat boundary condition on the outside using the built-in functions, and we could solve the simple 2-dimensional heat equation, and we got results that fairly closely matched what we saw experimentally. However, we do this in 2 dimensions, not in 3 dimensions, and 3-dimensional simulations on these sorts of complicated geometries is not quite there yet. There's another thing that we've also observed is the mechanical properties of these materials are quite strange. And the mechanical properties are such that if you take a piece of material out of one of these follicles, you change the relative humidity, you hold it at a given deformation, release it, it then keeps its shape. So you have a shape memory effect, and I won't go, due to the limitations of time, into this, but it turns out we can create a very simple differential equation which links stress and strain to an internal strain rate, and we could solve this using Mathematica to get more or less the same sort of behavior as we saw experimentally. This is not yet implemented in terms of a material model because, of course, we need to implement things like plasticity and internal variables and things like that, which we're not quite there yet. So the next step that we're trying to work on now, again, staying in 2 dimensions, is to go from these 2-dimensional images from CT scans or things like that to then automated 2-dimensional meshes, and then to run finite element simulations for solid mechanics. So taking a heat-based signal or a swelling-based signal to allow for expansion. And for example, here is a map of horizontal strain doing this. In order to understand the role of geometry, we've developed a very simple parametric model with a variety of different parameters where we can simulate different thicknesses, different lengths of geometries. So, and this can be used to automatically create meshes, for example, and furthermore, anisotropic orientation fields, because all of these plant-based tissues have anisotropic material properties, meaning that we need the full anisotropic elastic tensor in our materials here. And what we use here is the capabilities of being able to have a local orientation vector, which then defines the local orientation of the material properties, for example. And we're in the process of trying to do this systematically and get this moving forward. So again, in terms of time, I want to keep this fairly short. I think we're running out a little bit out of time, but to summarize, the FEM capabilities and the numerical solver has helped us understand, firstly, heat flow in these very strange temperature-dependent plants. It's given us an idea, an insight in terms of the mechanics of opening in 2D, these shape memory properties, so the material modeling. We haven't yet coupled any of these things yet, but we know from the previous talks that this in principle is possible, something still to do. And what are the future challenges? Well, the future challenges are to try to go to full 3D simulations, which we're not yet capable of doing. We want to have anisotropy in there. We want to automatically calculate orientations of the elastic tensors in 3D. We want to have coupled simulations. And in the long term, we also want to simulate how these things can grow and the development of pre-stresses and things like that. Now, we've tried doing this in other codes, and with say a lot of effort, we've managed to deal with isotropic material properties and to simulate so up to 3 million quad elements and an opening process of one full three-dimensional image. But this is certainly not yet possible in our current setup. This was done in a special setup that we're not doing. So we don't just do research. And then as a final quick slide, I just want to show you something that we can do, again, using the built-in functions of Mathematica that I use for teaching. And teaching is a very important aspect here. Is many of the people that I teach are biologists, geologists, and working with coding and working with modeling and working with physics is often quite scary for them. And in my teaching, what I do is I give them a basic introduction into using Mathematica, and then we go fully into trying to develop some 3D models where they can then start playing with things. And as the final example here, what we have here is a slice of a CT scan of one of my daughter's first teeth. So you can see the enamel on the outside, you can see the dentine on the inside. And we can take this, we can resize this again using built-in functionality to have a three-dimensional model, which is, we can then binarize it according to various values. So here now we have material, which is just ones and zeros. We haven't yet managed to fully automate for different material properties, but I think this is doable and possible. We can then mesh this, again, using built-in functionality. So here we have our tooth. We can then put in our three-dimensional mesh, and then using, again, built-in functionality, solve, and I won't do this live, but for example, here we can see the von Mises stress distribution if we take our tooth and we compress it virtually. And all of this we can do for people that are not yet experts in coding, not yet experts in solid mechanics, but it gives them an insight which is really unique. And I wanted to share that with you because I think it's a really neat tool to help students get into being excited about modeling and being excited about the possibilities of what we can do here. With that, I think I'm running out of time. I thank you all for your attendance, and I will try to answer questions in the chat afterwards. Thank you.
Thanks so much, John, and audience as well. So as John pointed out, these functions are good not only for research purposes, but also for teaching. So if you have questions about that, do feel free to ask questions in that domain about to any of our presenters. But since John mentioned it, I'll put him on the spot here if the audience want to direct questions about that. So thanks very much. Okay, so our next presenter will be Alexei Bulbich, who has worked in solid state physics and biophysics. And as I understand, we'll be talking about relaxation methods for solving PDEs.
Okay, do you hear me?
We can, yes.
Okay. Should I share screen or share presentation?
We recommend share presentation, share screen if that gives you any trouble.
Yeah. Okay, can you see my screen?
Yes, looking good.
Good. Hello. Then I am starting to make my talk about relaxation method for nonlinear stationary partial differential equation. And you know that nonlinear partial differential equations are problematic. Sometimes it is very difficult to solve such equations. Sometimes you can solve it right away, but sometimes no method helps you to solve it. And here I will present one very simple method, and I hope that you, just after my talk, you can start applying it. So what I would like that you take home with you, assume that we have a partial differential equation, a stationary one. Here L is the linear operator. U naught is the dependent variables or a set of dependent variables. X is an independent variable or a set of independent variables, and N is a nonlinear operator. And our task is to solve this nonlinear equation. Instead of solving this stationary nonlinear equation, we introduce a pseudo-time. And we introduce a time-dependent equation or pseudo-time-dependent equation. Here you see that we now have the equation which depends on time, and the dependent variable also depends not only on the independent variable x, but also on the pseudo-time. Now, here we have plus minus. This plus minus I will discuss a little bit later. The point is that as soon as the pseudo-time tends to infinity, these new variables u will tend to u naught. So the whole solution of the time-dependent equation will converge to the solution of the stationary equation. Now, why does it happen? Let us look at this stationary equation and time-dependent equation. And you will see that equation 1 is the condition of the fixed point for the equation 2. And this is the main point of my talk. So if you have a stationary nonlinear equation, you cannot solve it by more simple methods that I am offering you, then you just formulate the time-dependent equation, and the solution which you will get after a solution of the time-dependent equation will converge to the solution of the stationary equation. Now, let's come to a short summary. Short summary is that solution obtained by the relaxation method returns the attractive fixed points, if there are some. But the guarantee that there are some is that you are solving equation, the stationary equation, and it is from the very beginning, by default, it is assumed that the stationary equation has at least one solution. Then the solution corresponding to repulsive fixed point can be obtained by this plane with the plus and minus. By replacing plus by minus, you just get the dynamic equation that transforms t tending to minus infinity to t tending to plus infinity. Unfortunately, saddle points cannot be obtained. And finally, by trial and error, you should choose the initial conditions so that they lie within the corresponding basin of attractions. Now, let us pass to some examples. I will give you two examples, in fact, from my own experience, from the problems that I faced some time ago, and one example from Mathematica Stack Exchange. The first example is, you see this equation. This is a Ginzburg-Landau equation, but it differs from the standard Ginzburg-Landau equation by this term. This term V of x is the dependence of the factor in front of the linear term in this equation on coordinate, which is not typical for Ginzburg-Landau equation, so makes it non-trivial. So from the other hand, on the other hand, you can regard it as the Schrödinger equation, but the Schrödinger equation of a particle in a potential well. But this Schrödinger equation has the nonlinear term. Now the boundary conditions are in infinity and they are 0. And this potential well is the cosine hyperbolic to the power -2, and here it is shown. Now what we are going to do is we are going to go to the stationary, from stationary to pseudo-time dependent equation. Now you see that according to the rule, we added the first derivative with respect to time to this equation, and the dependent variable here depends now on x and t. So also depends on pseudo-time. Now the potential, we do not introduce pseudo-time into potential, but all other variables depend on x and t. And we, of course, introduce t into the boundary conditions. I will use three different initial conditions. One of them is simply a Gaussian exponent with the maximum in the origin of coordinate. The second is also the Gaussian exponent, but shifted a little bit from the origin of coordinates. And the third is a periodic function. Why I do this? Of course, in one solution, I will use only one of them. But I'm doing this just to show you how the choice of the initial conditions influence the solution. And now let us go to solution. You see here the equation. This here I highlighted the equation. And this equation, as you see, it's just what has been written here. It is nothing else that has been written here. And then solution. This solution I show you just to make for you to make sure that this solution is Ganz trivial. There is nothing special in this solution. It is just ND solve routine. And the only thing I do here, I put the boundary condition here at the finite distance from the origin of coordinate at x equal to plus minus 10. So here I will introduce initial condition depending of initial conditions that we will like to use. And here you see the plot of our solution. Yet what you are seeing now is just the initial condition. So this is a small bell-shaped function in the origin of coordinate. One here means that we used this first initial condition, and we start evaluating this solution. You see that the solution starts to grow until it grows to some height, which is about 1, and it stops. It gradually breaks and stops, which means that that the solution comes close to the fixed point. Let us try to look at the second initial condition. You see that it is located a little bit aside. We again starting running this time-dependent solution, and we get the same result. And you see, we try now a periodic boundary condition with the same effect. So in fact, what is not necessary will disappear, will just melt down, and what is necessary will grow up to form the solution that we need. In this situation, it is very important to control the convergence. It is very easy to control the convergence. You need to, you can control the convergence using one of the norms of the function. Here I used the Hilbert norm. And this Hilbert norm, you see how it behaves with time. Initially it grows, but then it comes to some horizontal asymptotics, and that exactly means that we came to the convergence. So as soon as we have achieved the horizontal asymptotic, you will decide that we have a converged solution. The second, I didn't tell you that the first example which I have shown you has something to do with the theory of domain walls. The second example comes from the theory of cracks. This example uses the same type of equation. It is, again, a Ginzburg-Landau equation with the same nonlinearity as it was in the previous case. But it is a two-dimensional one. And the potential, you see, potential is written here, and it is shown here, the form of this potential. So we can consider again this equation as a Ginzburg-Landau or as a Schrödinger equation in 2 dimensions with a rather strange potential, but in addition with the nonlinearity. Now, in this example, I would like to show you that sometimes we cannot solve straightforwardly this equation, but the method which I'm showing you offers you nevertheless the solution. Indeed, in this equation, in this situation, we are looking for the non-trivial solution. You can notice immediately that the trivial solution is indeed the solution of this equation, but we will be looking for the non-trivial solution. And here I just have written down the normal solution. So we will solve this equation within the square with the side which is equal to 2 times 120, and boundary conditions are 0 on the boundary of this square. Now here I just have written this equation, and here is again a standard and dissolve, and I'm again showing you this standard routine just to show you that there are no tricks. Now we have solved it, and just now I will try to draw it, and you see that the solution which I presented here is a trivial solution, which is not what we are looking for. So let us transition to the relaxation method. Transitioning for the relaxation method is to go to the time-dependent equation according to the general rule. So we write down this time-dependent equation. Again, I'm showing you to show that there is nothing special. The only special thing here is this boundary initial condition, which I have built in such a way that it would be in agreement with the boundary conditions. But if not this initial condition, then nothing special. And we again evaluate this thing, and we draw, and you see that as soon as we came to the relaxation method, we already obtained a non-trivial solution. I would admit that this solution is not the best one which we can obtain, but a better solution should use a better mesh, which here I just took just a standard. Now, there is a third example which I want to show you. Its example arises from the recent question which was asked in Mathematica Stack Exchange. Somebody asked the question how one can solve numerically such an equation. And you see that this is a differential equation. The boundary condition at one end is 0, and on the other end, at x equal to 4, the derivative is 0. We can go to time-dependent equation according to the general rule, and we can solve it. Again, it is a standard solution. And what we see here is this is the solution at different times t. The first of them is t equal to 0.5, it is a brown line here, and you see that at t equal to 1, this line goes downwards, then t equal to 3, still downwards, but then it comes to some fixed point. And this means that we have, at t equal to 5, we have practically achieved the solution. So that's all I wanted to tell you, and just I want to summarize. You just can use this method as soon as you find some difficult nonlinear partial differential equation. This method doesn't guarantee that in any case you will solve the equation, but it gives, I have a very good experience with it. It almost always gives me the solution. And to summarize, I would like to tell you that assume that you have a nonlinear stationary equation like this, that you make a step 1, you instead of this, you take a time-dependent equation. Then you make a step 2 by trial and error. You look for initial condition which belongs to attractive basin. And this is very important because you can go outside of attractive basin. And as soon as you found such an attractive basin, you make step 3, you solve the dynamic equation numerically, checking the convergence until the norm of the solution shows a horizontal asymptote. Done. Then it's okay. But this method has a penalty, and the penalty is that solution may take a considerable time. I would like to say that many ways in Mathematica bring you to the solution, like several heads of this animal, but one of them will sooner or later bring it there. Thank you for your attention.
Thank you very much for the excellent presentation. And as Alexei says, there's often more than one way of solving a given problem. And so the specifics might involve trade-offs in time or memory or other things. Thank you so much for the contribution. So our next presenter will be Jose Luis Gomez Munoz, who is the Data Science Program Director at Tecnológico de Monterrey, Campus Estado de Mexico. And we will hand the presentation slot over to Jose.
Hi, hello. Can you hear me?
We can.
Okay.
I think, still have Alexei's presentation showing, at least on my end. Okay, there it goes. And now we have yours showing.
Perfect. Okay. So, hello. Thank you for having me here. Thank you very much. I will present inverse problems in differential equations, just an introductory talk. So, in order to start, we are going to use first data and images from Jose Alberto Rodriguez, this paper about tumor cell growth modeling. And here I have a QR in case someone wants to use the cell phone to enter right now to see the paper that we are going to be using, just the data from this paper. So wait some seconds and then I continue here. So a simple direct problem, also known as a forward problem. All the parameters, coefficients, initial and boundary conditions are known, and the objective is to obtain the solution. A basic example is the Fairhouse model, the logistic growth. And here we have in the code a simple example solving it with the ND solve value. And here we have the differential equation. This initial condition is from the paper from the article by Rodriguez. And here we have just the plot of the solution. Yeah, just a simple solution to this differential equation. Let me also show another forward problem where we have now a more complex model, the Montreal growth model, where we have an extra parameter, theta, that in this model, the parameter theta controls the position of the inflection point of P of t. So here I am also solving this differential equation now with the parameter theta, all right, with the same initial condition, all right? And here we have the plot. In this case, I am using a very large value of theta to change actually the shape of the graph in a dramatic way. So let me go further here. Parametric end-insult value allows a more efficient work with numerical solutions that depend on parameters. As you can see in the properties and ratios section of the documentation help for parametric end-insult value. So here I am going to use parametric end-insult value. It has a very similar syntax to end-insult value. The difference now is that, well, we are specifying that we have 3 parameters, k, c, and theta. And also notice that when I use below in this manipulate the solution that was obtained here in solve p, notice please the syntax. We have solve p, k, c of theta to have the parameters, and then t to have the independent variable, right? And then here, the k, c, and theta, and the manipulate start with a value, for example, k of 0.2, c with a starting value of 1, and theta with start value of 10. And we can, of course, manipulate those c, k, and theta, and to see the effect that they have. For example, c, the parameter c, that is over here, is sometimes called the capacity of the, if this is the growth of a population, would be the capacity of the population final value, all right? So that all of that is for forward or direct problems. Now, in an inverse problem, we will need experimental data. We are taking this, we will use this data from the article by Rodriguez. Here we have it already, so I am just going to evaluate to have the data. And here we have a graph, and we can see that we have that kind of growth that might be modeled by this differential equation. So we are going to do that now that we have the data in the variable to more data. And here we solve the given some data. The inverse problem seeks to determine the parameters of the differential equation that will best fit the data. We first create a parametric function for the Fairhouse model. So here we have the parametric solution, let's say, that depends on the parameters k and c for this differential equation. And then we use nonlinear model fit is used to find the values of the parameters that best fits experimental data. They are the corresponding growth rate and capacity of the model. They have that interpretation. So here I just evaluate, I get some warning. From the beginning, first then we fit the parameters to the data that we have from the previous slide, all right, from the paper. And these were the values. Here I am extracting the values of the best parameters. K equal to 0.3, C equal to 7. And we also can see in the graph below where we are comparing the solution of the differential equation with the best fit parameters. We are comparing that to the data that actually the residuals have a pattern. The model underestimates the data for t less than 25. All the model, all the data is above the model, and it overestimates for t between 25 and 40. So we have some systematic residuals or errors, meaning that the model is, well, somehow performing purely. We could do better, and we actually will do better with the Monfron model, where we have now the third parameter theta, this one that appears here in the exponent, and will give more freedom to the model, more capacity. So let me evaluate here. Here we have again the numerical solution with parameters, and then we use a non-linear model fit to find the best parameters, the parameters that minimize some error, all right, to the data. Here we have the new values. I notice here I use the quiet in order to avoid the messages that appear. Then we have here the parameters 0.68, 7.42, 0.20, and we can see that we have now a best fit. All right, so that was simple examples with ordinary differential equations. Let's go now to something with a partial differential equation. Again, I am going to use data for another paper. Here we have again the sorry, can you hear me? Are you there?
We can, yes. Can you hear us?
Okay, thank you. I just lost my second monitor. I don't know why, but if you can hear me, I will continue. Thank you very much. Yep. There we have the paper that we are going to use. Here, the direct problem for this partial differential equation, in this case, is we have C of U and K of U as water capacity and hydraulic conductivity of a porous medium, all right? And U of X of T is a pressure head. Here we have a differential equation, typical differential equation for transport phenomena. Here we have the boundary conditions. And here we have first what we call the direct problem. The direct problem where we are supposed to know everything, and we just want to find U of X of T, the direct solution. Notice here, I want you to notice here how the condition on the derivative of X equals 0 is actually written in Mathematica here, this condition, right? So we have the first, the derivative with respect to the first variable of U, and all of this is an object, and then evaluated at 0t, right? Okay, so we will use an example, a particular example for this direct problem from the article, from the paper, right? And then we have a particular differential equation with some water capacity given by this expression, right? And for F with F of T given by this value. Of course, we can directly with NT source value get the solution. There we go. And we can graph. That's the direct simple problem. You can see, for example, the condition of U of 1t equal to 3t clearly reflects here in this graph. Let me do it a little bit larger. There we go. Here in this graph, we can see the 3t is of course here, as you can see. That's the direct problem, right? Now, we are going to generate some, we are going to simulate some experimental data as to actually find the, here from the article, the determination of hydraulic properties of porous media is often made by formulating and solving an inverse problem. In this case, in this example, the objective will be to obtain the water capacity from experimental measurements of this flux. So we are going to have data from this flux to try to get C of U, which is going to be supposed to be unknown. Now, our data or over-specified data, we are actually, in this case, going to generate from C of U, the one from the previous document. Let me go back. Here in the previous slide, I have this C of U. Yeah, I am going to use this C of U, this solution that we got, to get some, to simulate some experimental data. So this was obtained from the solution that of the previous direct problem. I did add a little bit of noise. Here you can see I have plus random variate normal distribution to have some noise. And this is, now we have here our data. There we go. That that is actually simulated, but imagine that is experimental and that we actually do not know the water capacity C of U, and our goal is to get it, right? To get the water capacity of the porous media. So that's what we're going to do now. We will approximate the water capacity coefficient, or which is actually a function of the pressure, depending on parameters W0, W1, and W2. This is just a simple functional form I am proposing. Of course, there could be other proposals. Then we will see to determine the optimal parameter values so as to minimize an error based on the very specified experimental data. So it's similar to what was done before. Here we have the inverse problem, all right, with now the differential equation where I am using now approx C instead of C, all right? I am supposed not to know this, and this approx C is given by this polynomial, and here you can see how it appears multiplying here to the differential equation. And so now we can create a parametric function, and now this time the parameters are W0, W1, and W2, the parameters that I introduced in the functional form of my water capacity. One more time, the same idea, nonlinear model fit is using the data, the supposedly experimental data or simulated. And now we are going to notice all of this expression because the data was not on U, was on this flux, all right? The constant times the derivative to find the values of W0, W1, W2 that best fit to this date, to the data. So let me evaluate here. It might take some seconds. Now, the model will give us a fit to this experimental data, but we will remember that it's not our goal. So in some seconds, I should see the answer. Let's see, still running. All right. I am waiting for this to run. If not, there we go. To give me the answer, to show it to you. There we go. So we have here the values of the parameters, all right? And here we can see that we have, well, a nice fit to our data for the flux, yeah? Now, remember that this is not our final goal. We were fitting to this data, but actually our goal is actually the water capacity. We can also see the solution of the differential equation, similar to what we saw before in the corresponding direct problem, right? But the real thing that we are interested in is the water capacity of the porous media, yeah? Now, here is our approximation. Now remember that our experimental data was actually simulated from this C of U. So this polynomial is supposed to be an approximation to this. Now, for what values of U can we expect that approximation to be, or should we expect that approximation to be good? Well, precisely the values of U that you can see here in the solution. Here is the values go between 0 and 6. So if I just graph the two functions between 0 and 6, then we can see that the parabola is actually making a fit to the value of the capacity. So it was we can compare the original C of U, which was originated to simulate experimental data, with the C fitted, and that was the idea of the inverse problem, that to obtain the water capacity or an expression for the water capacity. Of course, instead of, let me change here a little bit. Here, instead of fitted CU, let me write here fitted C only to have the expression fitted C. There we go. Here is the polynomial, and actually it will take more time, but we could do this for a polynomial of order 3 or a polynomial of order 4, and to, well, get approximations that somehow could be improving. All right, so that's an example of an inverse problem in a partial differential equation, where from experimental data we got the water capacity. There are more examples of inverse problems in the documentation center and Stack Exchange. There are examples, for example, in the documentation for the parametric n-dissolve command. There are examples also in the documentation for the find fit in the section applications, differential equations of the find fit command. Also in the documentation of nonlinear fit, you can see more examples. And finally, there are also examples, great examples in the Mathematica Stack Exchange. And well, this is what I wanted to share with you. How can we use the parametric n-dissolve command and nonlinear fit in order to get solutions to inverse problems. Thank you very much.
Thank you so much. So we had some audience questions. If you could please briefly show that very first QR code, audience.
Oh yeah, of course.
Yeah, audience, if you could get ready to screenshot that or whatever you want to do. Also, I've put a place where you can provide the links directly in the Q&A here. So audience, if you could just screenshot that real quickly if you were interested. We'll give you a couple seconds here.
There
and
is one
we'll also we'll also provide the links.
Okay, let me just go to the second one in case you also need. There it was. That's the second one. The second one that I will use.
Thank you so much. All right, so we'll give the audience a few seconds to do that. And again, we'll provide those links here in the Q&A chat as well.
Great.
Okay, so I think that has given the audience a chance to grab those. All right, thank you very much.
Thank you.
Okay, so audience, again, please put any questions into that Q&A chat and we'll get those links in there. So our next presenter is Pedro Flores Castillo of Celeros Flow Technology, the engineering director, who will be presenting his work.
Okay, great. Let me try to share my screen. Okay. So perfect. Can you see my screen?
We can. Looks good.
Okay, great. So this is a presentation on the Navier-Stokes solution paired with the heat equation to introducing radiation and condensation, basically to estimate what is the amount of water that we can condensate from a plate. And this is the topic of my thesis. There is a link to it, and you can actually see all the details of the thesis here. And basically, I won't show a very nice presentation in the sense that if you want to see nice graphics, etc., and the explanation in detail of what this is, you should be able to see it here. Also, I had the privilege to work with Mathematica to develop this PDE model graph, and they really did a very good job on basically explaining everything that I'm about to explain in a much more better detail that I can do today. But I think I'll go through one of the things that basically forced me to do some of the things that I did in my thesis. So this thesis is a work of 2 years of experimentation with Mathematica. I've been using Mathematica for over 20 years throughout my career, but this was kind of the most difficult project that I ever faced because it's a multiphysics problem, which involves several types of PDE equations. And I saw some questions in the chat about how big can you run a model. So some of these simulations that I was doing ran for 1 week. And at the end of the week, basically you end up with gigabytes of data, and that manipulation of the data is difficult. So one of the things that that this thesis forced me to do was to how can you manipulate such a big amount of data, and then at the end, when you finish up after a week of simulation, how do you keep the data so you don't have to run it again? How do you save it? How do you save it so you can reuse it and all of those things? So I think that's something that I think is going to be useful for you guys whenever you see something that is very time consuming, very demanding, that is going to take a couple of days to simulate. There's some strategies that you should use basically to save your data, to keep it in a separate file, reload it, So you don't have to rerun your PDEs. Some of these PDEs are very taxing for the computers. I start this on the Mac M1 processor. I'm on the Mac M3 processor. You can even on the M3 processor, it takes forever. On the M1, it just took really, really long time. So what is a PDE? It's a passive dew condenser. And what passive dew condenser basically takes liquid water, which is on the atmosphere, is evaporate the atmosphere, right, at temperature 1. And then the surface of the PDC is radiating to the space. And actually, when you look at the space, if you take a pyrometer to the sky, you'll see that it's always lower than the ambient temperature. So there's actually a temperature differential that is going to cause any surface to radiate to space. So this radiation is what makes this basically this difference of temperature in between the atmosphere and the surface of the PDC. So when you have your PDC lowering below the atmosphere temperature, you suddenly start to, under certain conditions, to condensate water, which is what we want. So why is water such an important topic? Obviously, water around the world, especially with this day and age where climate is changing rapidly, water could be readily available, water could not be available. So this is a method to collect water from the atmosphere without electricity. So basically what this does, you put your PDC, your passive dew condenser, you leave it overnight, and this only works at night because of radiation, which I'll explain later. Basically what it does is that it will radiate to atmosphere, cool down the surface, start collecting the water. So the water collection basically is very important. This is not a new idea, has been basically investigated for many years. Literature starts in the 1930s, where the first basically a scientific literature about condensation and the dew in the atmosphere came out to be. And then eventually in the 90s, there was a lot of work to investigate this. And now with computer techniques, obviously, there is an acceleration to try to optimize how much water you can collect out of the atmosphere more efficiently, right? So this is becoming an important topic, and obviously it's going to become more important to certain regions. So investigation is needed. So basically, these are the mechanisms. So there you have a radiation. You have actually multiple medias, and somebody talked about the different types of elements in a solution, and we'll talk about that as well. In this case, you have insulation, you have the condenser, you actually have the air around it, right? And with that, you have different elements that you'll have to solve differently, right? So one of them will behave differently, and how do you solve everything together into a single solution? That's the challenge. So this is kind of the mechanisms. You have the wind flowing overnight on the surface, and then you have basically a gradient of temperature on top of the surface, and this will allow water to condensate. And basically what the biggest mechanism is this simple equation. And I want to give thanks to my mentor, Dr. Basons. He's in France. He's the topmost expert on this topic. I have the opportunity to work with them for this topic. So basically what happens is that you have a differential temperature along this surface, which is you have an air interface, you have the surface which is cooling down, and then you have moisture in the atmosphere, which is going to touch the colder plate, and eventually water is going to start to condensate to generate the water. So this is very well studied. Now, what was not very well studied, how do you simulate this? So there was a lot of basically laboratory data, a lot of data out there to say we collected this much on this day and what, but there was not really a way to estimate with a mathematical method how much water you were able to condensate. So I'm kind of going to jump to the end of this conclusion. I was able to get to 99.9% accuracy on the data result that we got observed from the field. And that was basically this model. Basically, what it tells you is that it's a very good model of which really correlates to the empirical data out there. Now, I'm just going to run quickly on this. And one of the things that I was telling you about is you import previous solution. And I'm running live here. But if I were to run this now, I would actually be able to show you what this is about. But what I'm doing is basically throughout my presentation, I import the data that I run. And again, each one of these would take several days to solve. So obviously, I don't want that. The first thing is to defining what the geometry is. Basically, the second step is to generate the mesh. And the mesh basically is just a simple mesh. And then somebody asked about refinements. Mathematica, I mean, there is on the mesh area, there is a lot of techniques there to optimization of specific regions or specific materials there. So one of the things that you got to do, obviously, is set up what the materials you have. And then once you have your definition of the geometry, you do your mesh. And the meshing here, you have the air area interface, you have your condenser, and then you have your actual condensation surface. What is this red in below? This is actually an optimization technique. When you have air flowing from the left to the right, you don't care about this area. This is an insulator, so the heat transfer in here is not going to become important. Now, why is that important? Because if you introduce this with the Navier-Stokes equation, you're going to have turbulence. And to solve turbulence is just going to take even longer. It's not going to basically converge in some occasions, so you got to be very careful. So to avoid all that together, just remove the area is not of interest. And that's something also that is very important. When you have a very big mesh and there is no areas of interest, just remove them. And that's something that Mathematica can do. Nothing else can do that in my experience. I've been using ANSYS, COMSOL, all the different softwares. And yes, one of them is $100,000 a year license. Mathematica is very affordable, something that you can optimize to the nth degree, which you can't really do with other software packages out there. So that's why I just went to Mathematica, because I knew that I could tweak this to the nth degree that I needed for my research. Now, one of the things on this one is, as I was saying, Mathematica will solve anything. Now, the question is how long will it take? And that's where you have to come in and say, how do I optimize my technique? So why did I don't care about this? You can see the mesh elements. These are coarse. These are very fine. And when I really get a very fine, refined mesh on the area where the interface is, that's where the most interest is for my research. Here, basically, you'll see later, I want to remove it from the mesh. So that's, with that said, you see the different colors represent the different characteristics of the materials. Now, on the Navier-Stokes equation, it's a very tricky equation. You got to ramp it up, and you see this from through the PDE solution. You got to ramp up the function. You cannot just give up a solution. You got to start from zero and then slowly ramping up. Now, one of the other techniques that I use to really get this solved is that when you try to solve the Navier-Stokes equation at higher velocity, you will introduce a lot of turbulence, which turbulence, again, is going to be a problematic issue. At the surface of the PDC interface between the surface and the air, basically is a linear solution. You don't have to take into consideration basically this turbulence. So one of the things that I did is I was able to solve the solution of the Navier-Stokes equation up to a certain velocity, in this case 1 meter per second, but the actual data came at 10 meters per second. So if you solve the Navier-Stokes equation to 10 meters per second, it will not solve. It's just because all these turbulence that I'm talking about now. So I was able now to get down to a solution of 1, but how do I get the results to 10? I basically use linear interpolation to get an approximate solution to the Navier-Stokes equation. Guess what? After I finished my research, I found out that the Manhattan Project actually used that technique because the neutron calculation from the atomic bomb was so complicated they had to linearize. And so this linearization technique is something that I got to think about when you got to do a lot of difficult equations to solve. You may be able to just solve a certain portion and then escalate to the remainder of the solution. Now, the other technique that I use is basically I broke down this into several steps. So first of all, solving the Navier-Stokes equation. Second is solving the heat equation. Third, solving the condensation. So the radiation, then solving the condensation. Now, you could do this all of it at once in a single equation, right? That's a pair solution, but guess what happens? It's just gonna take even longer. It may not solve, and it just basically becomes very complicated to solve. So the solution here, and you'll see later, is that you solve one, inject those results to the next, inject those results to the next, etc., until you get your solution. And guess what? The results are the same. Now, why is it important? Because if you solve for second one, you finish, you inject those to second two, you're basically very close in the time frame, basically, to get a good solution. So, okay, so I'm defining all my variables in here. You'll see all the properties for all the materials. So I define my Navier-Stokes equations in two axes, X and Y. continuity equation as well. You could solve this in 3D as well. We did that as well, but we found that the results were the same. So it was not worth the time computing effort to do it in 3D. So, okay, so in 3D is basically the same. The simulation is the same, except that you define your solution in a 3D space. The mesh is in a 3D space, etc. Now, when you have your inbound conditions, obviously you have to have a 2D inflow of air to define that. And this is the result of the 3D simulation. Again, when you want to do that, the result of a 3D versus 2D is just going to be basically multiplied by 10, potentially, or more. Okay, so that's why a 2D solution is something that you got to investigate. Now, basically, what I do here, I get my results. If you're running for 24 hours, you don't want to be losing your results. So I save my results to a specific file, and that file then I retrieve when I needed to work with it and do all these graphs. So this is the solution, as you can see here. You get from left to right, and you can see here, I'm still solving this, but I'm saying that this is a super dense thing, which is basically a solid. So there is no movement of air. All of it is just wind is just moving. And then what is important here is just to qualify exactly what is the velocity of the wind at certain different distances from the plate. And then from here, you see the different curves at different distances. And you can see at the boundary, you almost get a zero solution of velocity. Okay, so this is kind of what it just basically the solution of the 3D, as you can see here. Eventually, this is just a slide, and then you see what happens. You get this, which is not something that I care about, and that's why I will remove it next. Okay, I'm just going to pause this. The heat transfer solution. So now I finished the Navier-Stokes. Now I'm going to solve the heat equation. What do you need on the heat equation? You need to inject the velocity of the air, right? Because this is a convection happening. Basically, you're transferring the heat from the wind to the plate. So that's why you got to take that in. That's part of the heat equation. You'll see it here. But the important thing that I was telling you, I was able now to remove this section of the mesh. Now, as I said, I was always been working with simulation for many, many years, over 20. And with ANSYS and all of the other softwares, it's very difficult to remove meshes and whatnot. It just becomes very complex. On this, very simple. You remove, now look at what I did. Since I already have my Navier-Stokes solution, now I take another mesh and I inject the results into my new mesh. The results that I inject are only the most important here now that I care about. It's just the area next to the plate, right? And the plate itself. And that's where I get a better refinement. Now I went from 70,000 elements to only 3,000. This is very important because now you're reducing the solution speed very significantly. Now, this next section, and obviously you will be accessing this data, this Mathematica notebook, but it will explain to you why the Stefan-Boltzmann equation is involving here because of radiation, and then you not only do it in a single plane, but you got to do it in 3 planes, and then basically that's basically how much radiation you put to space, right? And then something very important in Mathematica. So Mathematica is an infinite tool to do so many things. Anything you want, you will be able to do. One of the things that I was able to do is basically take weather data from anything, anywhere in the world, any day, and basically I can take that data and simulate in my system how much water could I condensate. Now, this is important because if you want to see, okay, can I deploy this somewhere in the jungle? Is this going to be effective? Yes, okay, take some sample data and it will tell you how much water you could collect on certain days, right? So I think for water condensation studies, this is something very useful. You take basically your latitude, your longitude, where are you located, and it will take Mathematica can import that weather data to your system, and then basically you can run it from there. It has very good weather data, temperature, velocities, a lot of wind speed, pressure, etc., that can be used to this type of simulation. Now, what I did next is I was basically just playing with it to see where could I calculate this from around the world, but the real data was taken from Morocco. And this is data that Dr. Vason provided to me, basically in a study that was done in there. So the data is then injected directly from Excel to Mathematica, and then, but Excel is discrete data. So now you want to convert that into an interpolated function, and each one of these curves is interpolated. Now, and the next step is basically take your data and make it into a nice function. Now, if you want to this data to be injected into the heat equation, it better have no steps, right? It has to be a smooth transitions, right? That's something that you got to think about. When you inject in real data, has to be smooth transitions. Otherwise, you're going to have trouble solving it in Mathematica. Okay, so final radiation model. So radiation is important basically to know at what time you can start collecting water, at what time you will stop collecting water. And obviously, as soon as the sun goes down, you will start collecting water. Now, if you live in coastal areas, you'll see this every day in the morning. You'll see water condensing in your cars, in your windows, etc. And this happens around the world. And under certain conditions, you can even generate water in the desert, because the desert just gets so cold at night because of the exchange of radiation, and there's a little bit of humidity. You can condense water there. And that's when you think about it, how do plants in the desert work? One of those spikes that you have on the cactuses are exactly designed for that, to collect water through the atmosphere to radiation. That's something that's been investigated on this topic. And it's super interesting to take the shapes of nature and how you can use them to make a better condenser. Okay, so let me just run quickly here. So wind interpolation, so I'm creating all my equations, and you can see here, I just take my extrapolation. What I was telling you about, I was able to calculate the Navier-Stokes equations to 1 meter per second, but the data comes in at more than 1 meter per second, up to 5 or 10 meters per second. So now I need to extrapolate that. So I generate an extrapolation function, and then you have it. So basically what it does, now you are able to get any result of the Navier-Stokes equation at other velocities, right? You cannot extrapolate too much, right? You need to be careful, because if I say that the actual wind conditions were 100 meters per second, obviously this is not going to be correct. But in the small range, you could use the linearization techniques that I'm describing. Okay, so the first method of solution is basically, as I was saying, you take the Navier-Stokes solution, you inject it the heat equation, you basically calculate your temperature, then you calculate the heat coefficient that I was telling you about, that is so important. From there, you can calculate water condensation. Okay, so that's what I'm going to do now. I take my results, I inject them into the heat equation, and then I solve it, right? And I get some results, right? Okay, and with this, this simulation will take literally 24 hours to solve. So I don't want to do that. And you can see already the progress. If you have more than 3,000 elements, it's going to multiply that by the number of elements you have. So if you have 3,000, 1 day. If you have 6,000, 2 days, etc. That's why the optimization of the element is so important when you have complex problems. Okay, so again, I take my solution. I don't want to be wasting any time, so I take my solution so I can reuse it later. And then eventually I get to visualizing the data, and this is the data. So you have your, throughout different days, you have how much is the wind velocity, the extrapolation, what is the velocity on the surface, and then from there you can calculate what is the temperature on the surface. And this is the due temperature. Basically, below the due temperature, you start collecting water. Above the due temperature, you don't collect water. So then from here, you calculate the heat transfer coefficient, which is the most important parameter to estimate how much water you can condense. And here, you see here, basically, this is the Navier-Stokes solution. This is the heat equation solution. And you can see here at this specific condition, which is zero wind, at zero, you can see a nice boundary of temperature, how the heat is transferred to the air surrounding the PDC. So that's very interesting. Okay, so then so I don't waste any time as well. I keep saving my results, right? So I can reuse. And then eventually you start calculating in more detail the water condensation. You have several models, but one of them is that when you condense water, the heat will heat up. So water condensation, instead of cooling down, is going to heat up the plate, because it's taking away heat from the water and transferring to the plate. So that is very important, because when you're thinking the plate is going to remain at a certain temperature, in reality, no. As you condense water, the plate is going to heat up slightly. So that also needs to be introduced as well. So now what I do, I take that and then I solve, and I get 24. The actual results from the field, 22.1. So this is about 10% accurate. So this is not good enough. I gave this to Dr. Basin. He said, no, this is not good enough. You gotta get a better. I'm an engineer. As an engineer, this is perfect. As a scientist, this is absolutely crazy. You cannot do this. So he said, go back and inject the water, the heat condensation. the heat of condensation. So that's what I did. So now I take basically, this is the data, and you can see how accurate this is. The dotted points are the data. The projected temperature is the green data. This is the simulation, and this is the water as it condenses through the night. Okay, so what is the next strategy? So you take your Navier-Stokes solution, you inject it to the heat equation, you get your temperature, you get your the transfer coefficients, you inject the heat of condensation to your heat solution, and then get a new temperature. Basically, you're adding to the temperature. This is something that you could not do in ANSYS, you could not do in COMSOL unless you're very sophisticated. So in Mathematica, it's simpler. You think about it, and you just basically use the data and reuse it very simply. Okay, so the next step basically is solving the equation. This takes a long time, several days to solve, depending on how large is your mesh. Okay, so I'm just gonna get to something cool as to how do you see this progressing throughout the day. And it basically, you can see this line is this is the dew temperature. As the temperature goes down, you start collecting more water. This is the latent heat of condensation. This is water accumulation. And you accumulate very little water throughout the day, but you can see some areas of the plate are not accumulating because they're above the dew point, and some areas are accumulating more. So this is something that basically, this is the novel application of my thesis. This was not comprehended as to how you could condensate water throughout the plate. Okay, so eventually you get to the next step. Okay, and then okay, so the end result is 21.5. The actual result is 21.4, I believe. So it's very close to reality. And then finally, how this is impacted by different factors. I'll show you quickly to what this is the implication. So you have the optimal angles, you have the optimal lengths, and then you have variation on the height, and that will determine how much water you can condensate. The theoretical maximum is set to be 80. The data that I have is the maximum you can condensate per meter square is about 0.4 liters of water, which is a lot. When you think about 4.4 liters, it's for a single 1 meter square plate is significant. Okay, with that, I finish up my presentation. Thank you so much.
Thanks so much. We appreciate that. So we had some good audience questions about parallelization and how things like that can be done. So speakers, if you have experience with that, and Oliver perhaps should also want to comment. I put some guide pages about.
You want me to answer or?
So just in the Q&A chat there, for the interest of time, we'll not do that.
You want to jump to the next speaker, or you want me to answer that?
If you could do that in the Q&A chat, that would be fantastic. Thank you. Okay, great. So our next speaker will be Dr. Richard Gass, who is joining us from University of Cincinnati, emeritus professor in the Department of Physics.
Okay, so do you hear me, and do you see my screen?
Yes, we do.
Okay, thank you for coming. So I want to talk about solving Maxwell's equations, which, as Oliver mentioned, are computationally intensive in their full form. And one way of doing this is finite difference time domain methods. So I want to talk about implementing those in Mathematica. And let me hang on. Let me go to the next slide here. So here are the equations we want to solve. And these are in their kind of full-blown generality with possibly electric polarizations as well as magnetic moment density, although I'll mostly be talking about the free space case. So in free space, these simplify since the polarization and the magnetic moment are zero. Still, solving them is slightly tricky because we have to maintain the divergence conditions. We want the fields to be divergent free at all times and at all points. And there's a method known as Yee's method, which automatically does this. And the key to Yee's method is that we're going to stagger both the spatial and temporal derivatives by central differences, but we're going to stagger them so that the electric and magnetic fields are interleaved, and these are interleaved in both space and time. So for example, we'll start with a one-dimensional case. For the time derivative of the electric field, we're going to step forward by delta t over 2 and backward by delta t over 2. Whereas for the spatial derivatives, we're going to step forward by delta z, and of course, delta z is related to delta t by the speed of light. Okay, and then we're going to do exactly the opposite thing for the H field. So we're solving the electric field at half integer time steps, but integer spatial steps, and vice versa for the magnetic field. And this means that each field component is actually surrounded by the components needed to calculate its curl, which I'll show graphically or visually in a moment. And Yee's method guarantees that the divergence conditions are satisfied, so that we only need to solve the curl conditions. A disadvantage of Yee's method, however, is that it does have numerical dispersion, meaning that if I run it and look closely, I'll see that the wave is dispersive even in vacuum, even in free space, which we know it shouldn't be. You can control this dispersion by using finer grid spacing, but of course that increases your computation time. So the way you visualize what's going on is known as the Yee cube, which shows at what spatial points the fields are evaluated at. In the presentation notebook, which you can download, you can pick this up and rotate it to get a better feel for the spatial interleaving. Okay. So I want to start with the simplest possible case, which is one-dimensional propagation. So I'll pick the direction of propagation to be along the z-axis. And then in one dimension, we only have, two coupled differential equations to solve because the divergence equations are solved, are maintained automatically by this method. Okay. So let's do a simple example. I want a wave that propagates in free space for z less than 0, and then hits some medium, okay, with a permittivity with an epsilon that's not equal to 1. So you could think of this as a wave, striking glass, for example. And I've plotted the situation here for the variation in epsilon as a function of z. We're going to solve these equations on a grid. And the rule of thumb is to pick a grid spacing between 1/10 of a wavelength and 1/40 of a wavelength. And for this example, I'm going to start with a Gaussian for the E field initially at t equals 0 and no H field. Okay, so the code's given here. I generate a grid. I'm going to run it from z equals -8 to 8. Okay, I've plotted the E field at t equals 0 here for you. We only have a component in the x. Okay, I'll implement the spatial derivatives by using list rotation. Okay, this is a very efficient way of implementing a derivative in Mathematica. And we'll rotate right for the spatial derivative of the magnetic field, and we'll use a left rotation for the spatial derivative of the electric field, and that ensures that we get the proper spatial interleaving. Okay, so in Mathematica, this interleaving is very easy to implement, and the boundary conditions imposed by list rotation are periodic. So it's important to recognize that at at some time, your your simulation, your calculation will run off the end, right, and wrap around and will no longer be valid. So you have to pay attention to that. So I'll step forward in steps of delta t over 2. I'll pick t naught to be 0, so time is n delta t over 2. We're going to use an explicit method for solving the equations, and explicit methods are only conditionally stable. So we have to be careful that we satisfy the Courant condition and take our time steps less than or equal to delta z over 2c. In the units I'm working in, c is 1, because I've taken both mu naught and epsilon naught to be 1 in a vacuum. Okay. So delta t will be delta z over 2. And in any of these calculations, you have to think about what your physical units are. So we need 10 to, say, 50 grid points per wavelength. And thus, if we're going to look at, say, red light propagating over 1 millimeter with 10 grid points per wavelength, the grid spacing, the physical units on the grid spacing are 65 nanometers. Okay, we need only about 15,000 grid points, and the time steps are about 1 times 10 to the minus 16 seconds, and we only need a little over 3,000. So this is really easily doable. If you wanted to do an FM radio wave with a wavelength of 3 meters, and you wanted to follow it for a second, which of course is a huge distance, you'd never really want to do that. You'd need 1 billion grid points, so that would be a problem. Okay, so the code's all in the notebook here. I don't really intend to go through it, but you can see in the interests of time, you can see here we implement the derivatives with a list rotation. And you can also see that, in fact, there's not much code here. Right, Mathematics is a very efficient and, shall we say, terse language. In fact, most of this code is just for the visualization. Okay, let me step forward to the next slide. Okay, so here we see what happens. Let me crank this back to the beginning. Okay, so red is the H field, which gets generated because we've got a time-dependent E field. You can see that we strike the barrier. The results look reasonable because speed of propagation then in the barrier, where we have a non-zero, an index of refraction that's not 1. Okay, has slowed down. You may initially ask why the E fields and H fields are the same order of magnitude, because you, of course, expect a suppression by a factor of C, but remember in these units C is 1, so there is no suppression here. Okay, here's a more complicated example. Here we have both initial Gaussian E and H fields. The code is all here in the notebook that you can look at if you want to download it. But what we have here is electric and magnetic fields propagating onto a dielectric comb with 61 teeth. Okay, you can see the propagation here. To give you a feel, the computation time on my laptop, which is an M1 Max, is about 42 seconds for this. So, let me advance the slide. Okay, so we can also, of course, do other polarizations. So if we do circularly polarized waves, we now have 4 equations that we need to solve. The propagation is still, of course, in the z direction. Electromagnetic waves are transverse. Okay, so we have to now specify 4 initial conditions, which I've taken to be sine waves modulated by Gaussians with a slightly smaller H field and a phase difference. If I pick the phase in the phi x to be pi over 2 and phi y to be 0, then I get circular polarization. If you simply change this, which is trivial to do in the code, then of course you can model elliptical polarization as well. So here we see, right, the circularly polarized waves hitting. Oh, and I need to, sorry about that, I need to turn the magnification down here so that you can see everything at once. Okay, so here, of course, I've got 4 fields, right? Electric fields in the X and Y, okay, and magnetic fields also, right, in the X and Y. So here you see the propagation of all of them. And for this, the computation time was just under a minute, so, right, doesn't take too, right, terribly long. Here I'm showing you another view where I show you the E and H fields in the X direction, right, at some essentially arbitrarily selected time, right, across my whole grid. Now, it is, of course, of interest, right, to look at the 2-dimensional case. In the 2-dimensional case, we can break the equations up, okay, into the TM mode and the TE mode. So I've listed them here for both modes for you. I'll focus on the TM mode here. Go to the next slide. Okay. And I'm going to scatter off a dielectric barrier with an epsilon of 5. Mu is 1, so the index of refraction will be the square root of 5. The code for generating the barrier and the initial conditions is here and hidden, but is available for you to play with in the presentation notebook if you download it. Okay, there are a few technical details here, most of which I'll gloss over. Once again, the derivatives are implemented by list rotation. We now have 2-dimensional derivatives, so whether you're taking a step in the X or Y depends on whether you're rotating row or columns. All the details are in here. For the boundary conditions for a perfect conductor, we have to set the electric field to 0 at the boundaries. So you have to think about what you want to do there, but the details are given here. You don't have to worry about the boundary conditions for the H field because those are calculated from the E. The H field gets calculated from the E fields, and so long as you impose the boundary conditions for the E before you calculate the H fields, then that's automatic. The other technical comment is on plotting. The field is 0 over most of your domain of interest. It's very expensive to list plot a function like that because you're plotting at every grid point, most of which are 0. So it is much faster in terms of both memory and CPU time to make an interpolating function and then let plot 3D do its thing. Details are all in the notebook, but in the interest of time, hidden here. Okay, so here I'm going to propagate a wave, electromagnetic wave, through a dielectric slit. Okay, what I'm plotting here is the intensity, so this is what your eye would see as the wave moves through the dielectric and diffracts through here. Okay, so the results certainly look reasonable, but you should ask, of course, how accurate they are. And one way to check that is to calculate the energy and check energy conservation. So let me go to the next slide. Okay, so here I've plotted for you the initial energy, or the energy divided by the initial energy. So in a perfect calculation, this would be, right, a straight line across here at 1. Okay, I've done this on a fairly small grid, 401 by 401. You'll see you do pretty well, but, right, here energy conservation varies by about 2%, okay, 2.5%. You're worse when the wave is partially in the dielectric and partially not. Okay, you can fix that by going to a finer grid, of course. Okay, so here's the last example. I'm propagating now, right, 2 Gaussians through, right, essentially a double slit. Okay, and you can see the fairly complicated diffraction pattern. Once again, I'm plotting the intensity. And once again, you should ask yourself, right, how well do we do with energy? Okay, for this example, I've run on a 400 by 400, well, 401 by 401 grid. Okay, and right, you can see you do about 1.5%. If you double the grid, which of course ups computation time by a factor of 4, you can see that you are much more accurate. If you used a higher dielectric material, you would get worse energy conservation, particularly in the cases where part of the wave was inside and part of the wave was outside the dielectric. You would need to use a finer grid, and thus it would cost you more in terms of computation time. Right, on a 801 by 801 grid, this calculation takes a couple of minutes on my, right, M1 Mac. You can pretty easily extend the code to do the 3-dimensional case, but you should be aware that the 3-dimensional case computation times are going to go up considerably, you know, to at least hours, and depending on your calculation, maybe a couple of days. Then there are also, the last slide, I've got a list of references here, right, if you're interested in exploring this, okay, in more depth. Okay, there's some applications for cloaking as well as a bunch of, right, nanoscience applications here. So thank you very much for your time. And with that, I'll conclude, and I'll be happy to answer any questions in the chat. Or you know, my email is on the notebook, on the presentation notebook, so you're welcome to email me if you like. And with that, I'll turn it over to John to introduce the next speaker.
Thank you so much. All right, so our last but certainly not least presenter will be Paritosh Mukasey, joining us from University of Mississippi. So I'll turn it over to Paritosh.
Hey guys, thanks for sticking around. I want to talk to you about a new method that I've been working on for solving just general PDEs in arbitrary domain using a quadratic optimization framework. This is still work in progress, but I thought I'd share some interesting results associated with this work. So the first and the most obvious question is, well, we're interested in solving PDEs in arbitrary domain, but we have ND-solve already. Every single person in this colloquium has already shown you that we can solve a lot of stuff with ND-solve. So why bother? I mean, we have FEM available. There are a couple of disadvantages, or rather limitations, not disadvantages, limitations. ND-solve using the FEM method, you can solve the PDEs in 1D, 2D, and 3D in arbitrary domain. You can mesh it up and do all kinds of stuff. The other method that is currently available is using finite differences, and you can solve those problems in arbitrary dimensions, but the domain has to be rectangular, and it has to be time dependent. You actually can't really solve an elliptic PDE kind of a problem using finite differences directly using ND-solve. You have to do a little bit of coding yourself. So my thesis was essentially, I don't want to use FEM because just because I'm a snob, and so I'm like, can we solve finite difference use finite difference methods to solve PDEs in arbitrary domain? Well, yes, you can technically. There have been hundreds of literature written since the 1960s on how to do that, but there's always some little components that are always missing. And so I wanted to present a way to basically incorporate arbitrary domains by still using the advantages of finite difference methods. So let's get with that. So finite differences in ND-solve is basically you have a derivative that you need to approximate based on the function values at certain structured node, right? So you have at x0, x1, x2, you have function values, and to get a derivative, you basically take a weighted sum of those function values, and from there you're able to get the derivative. And if you want to get, so in one dimension, it's pretty straightforward. You have very efficient formulas. Look up Ben Fonberg, and you'll see extremely efficient formulations of how to get finite difference approximations. And if you want to extend that to a 2D, 3D, ND, you simply just have to take a bunch of Kronecker products with the identity matrix in order to get a first-order derivative approximation in 2D or 3D or whatever. So this is all very well established, and really there's nothing more to be said about finite differences. It is extremely accurate. The more important thing is you can do a lot of math and error analysis associated with finite differences because you get an order approximation, and you know exactly how the error and the truncation errors work. So a lot of research has been done in finite differences. So let me just give you an example. Now, the thing is that we really don't have to code anything. Finite difference approximations has existed in ND-solve since Rob Knapp first wrote the ND-solve, or rather Mark did. So let me just take you through one simple example. Here we have an exact solution. We're going to solve a partial differential equation, which is an elliptic PDE. In 2D, I have the exact solution, and I'm just going to construct the right-hand side from the exact solution to get the right-hand side. I'm going to divide the x and y grid in which goes from 0 to 1 in 40 grid points in x and y direction, and just generate a grid. And then from there, just extract the domain boundary, which is at zeros and the ones in the x and y direction. Now, this is the part wherein all the magic happens, which is you just use the built-in function ND-solve. In the context of ND-solve, you use this function called finite difference derivative. You provide it with the x grid and the y grid, and you can specify difference order. You can go 4 to whatever. You can give pseudospectral, and you can even say, hey, listen, my boundary conditions need to be, my derivatives need to be in the periodic domain, so you can even incorporate that. And then from there, you can extract out from this object the differentiation matrix. So in this case, I'm going to extract out the identity matrix, which is kind of silly, but I decided to do it anyways. The second order derivative in the x direction and the second order derivative in the y direction. Now, one of the things with these finite difference approximations is that the matrices come out extraordinarily sparse. Not only are they sparse, they're actually structured arrays, which means that you can actually employ very specific, efficient algorithms to solve these systems when you finally assemble them together. If you take just a second order finite difference in 1D, you get a tridiagonal system. We know how to solve these extremely efficiently. You don't even have to construct the matrices. You just need to get the values in the diagonal and the terms. So in this case, in this one line, I've constructed the Laplacian approximation, which comes out as a sparse array. Once I have this Laplacian matrix, I can apply my boundary conditions, which is, in this case, it's a Dirichlet boundary condition. So I'm just going to apply the identity matrices, and then apply the right-hand side with the associated boundary conditions to the final system. You end up with, for the elliptic PDE, it's a linear PDE, which means you can solve it just using linear solve. You get you just invert the Laplacian and with the right-hand side, and what you get back manually is essentially an interpolation, a solution which you can generate an interpolating function from. You can visualize this, and there's a result. Really nothing spectacular about this. This exists in the documentation in one form or the other, or you can just use this or you can go to Stack Exchange. There's plenty of examples that demonstrate how this is used. Well, this is all fine and dandy if you're dealing with a rectangular grid, but what happens if I've decided to choose a domain like this, and for some absurd reason, I insist that you must solve it using finite difference methods? Well, how do we go about that? And the rest of the talk is going to be essentially how the process that on how one could achieve this one possible way. Okay, so you start with so this is my arbitrary domain. We start with a boundary discretization of that. Then what we are going to do is we are going to apply a background grid on which the PDE is going to be solved, and that background grid is going to be a tensor product rectangular grid. So that's our background grid. Our PDE is going to be applied on that, and our domain lives inside of this this extended domain. Now, I want to point out at this point in time, the viewers might be thinking, "Hey, this sounds awfully familiar, like an immersed boundary method or some one of those variants of that." It's slightly different from that. I'll explain that as I walk you through the math of it. So first step, we have a domain. We discretize it. We are only interested in the boundary of the domain, and those are the node values. We embed those boundary nodes inside of a larger domain over which our PDE is going to be discretized. Okay, that's our step 2. Once we have that, then we are left with the critical part. This is, in my opinion, the missing link that ties it all together, which is that we have these arbitrary boundary, these points from our arbitrary domain that are sitting inside this structured rectangular grid. And the question is, how do we incorporate or account for these boundary points so that the appropriate boundary conditions at those nodes are evaluated correctly? And the way I decided that to approach this was to use mesh-free methods. So what exactly are mesh-free methods? So this falls under a slightly different area of approximation theory, which is unstructured approximation, wherein you have a whole bunch of unstructured meshes, you have points, and the way you want to solve that is you get a hold of the nearest neighbors, and you need to compute these weights W to get an approximation of whatever operator you want. So the way this is done is traditionally it is done using radial basis functions. So just to give you a quick tutorial on that without going into too much details, let's say that you have a whole bunch of function values fi at a bunch of random node locations x and y. In this case, I've decided to use 2D, but it could be in ND space. What you want to do is find an interpolant, a smooth interpolant that interpolates that the interpolant is exact at the function value at the x and x locations. And so that's how the way you define this interpolant is through the summation term, wherein you have a bunch of analytic functions phi, and you have a bunch of unknown coefficients lambda, of which you need to find those values lambda. Those phi are defined, user-defined functions, and they are called radial basic functions, which are just, it's a single function that you shift in space. So this radial basic function, you could have, there are a whole array of that, and I'll talk about that in a bit. Once you define what your radial basic function is, from this, you can generate a whole set of bases. So from this basic function, you generate a whole bunch of bases, as shown over here, using the norm, Euclidean norm. And from there, once you have the basis functions, you basically have all the information needed to solve the problem, which is essentially just solving one system of linear equations to get this unknown coefficient lambda. Okay, I'll get to some more details in a bit, but this is basically the underlying theory behind mesh-free methods. What are these basic functions? I mentioned these basic functions over here. What are they? Well, we choose them such that they have some very specific properties, especially because you need to perform an inverse operation, and you want to make sure that the matrix that you end up with is symmetric and positive definite, so that an inverse is guaranteed and has got all sorts of good properties. And so based off of that, a number of different radial basic functions can be chosen. I have listed some in this table over here. There's inverse multiquadratic. The most famous one is the Gaussian. There's an inverse multiquadratic. Multiquadratic has been used significantly in topography and such. Different applications choose different methods. There is no hard and fast rule. Each one of them has their pros and cons. Once you choose what your radial basic function is, and you can then generate this approximation and solve it. Now, most of the time, what happens is that people they tend to add a set of polynomial bases so that you can get, so that if your underlying function happens to live in the same space as a polynomial function, if you add that additional term over there, then you are guaranteed that the radial basis function approximation that you are getting of the continuous function approximation will faithfully reproduce that polynomial term. That's why you add that polynomial term. So in 1D, it's just 1x squared. That's the value of the p. In 2D, it forms the complete basis. 3D, so on. Okay, so polynomials, right now these are Taylor polynomials. You could use Chebyshev polynomials or any other variant thereof. But basically, this is the underlying. This is the form of the basis of your underlying interpolant. Okay, so how are we going? How do we? Once we get all the basic functions, we figure out what the polynomials are. What we end up with is this following system of equations. Okay, so on the left-hand side, it's known. Phi is known, so you can generate a matrix out of it. That's your matrix A. Polynomials are known. All that you need to compute are these lambdas and these alphas. And that turns out to be just solving this system of linear equation. This is symmetric, positive, definite, depending upon the type of basis functions you use. You solve this, and you get your interpolant. At this point in time, I do want to point out that at no point in time did we talk about a mesh, did we talk about any grid, none of that. These are just nodes that are scattered in your n-dimensional space, and you're just getting an interpolant approximation. And this is the way that is done. Okay, so once we solve this, we have an interpolant f that represents our underlying unknown function. And if you want to, because you know everything there is to know about this has been computed, you can then take derivatives of this, right? And you can use that to generate whatever derivative approximations. So you can technically use the same principle in order to generate your weights for approximating your differential operator on these scattered nodes without any information of the connectivity information, as it is typically done with finite differences or finite element or finite volume methods. Everything is arbitrary domain. using this this approach, you could get approximations of your differential operator using only these node information, and this is how you would do that through this. This is the math part of it. So using this, once you have the derivative approximation, you basically are in a position to get all the information you need in this n-dimensional space associated with your underlying function f. Okay. This brings us to, so why did I show you this mesh tree method? It's because we're going to use this mesh tree method in order to connect, I'm going to have to go back a few, connect the boundary information to the underlying grid information. That's the basic part of it. So this green dot is on our boundary. We need to approximate the derivatives and the function value at this green node as a function of the underlying tensor product grid that we have generated, our background grid. And we use mesh tree methods in order to do that. Okay. So now that we've decided that, okay, the mesh tree method gives us a way to generate information about the boundary nodes as a function of the background tensor product grid. We now are left with the question of how do you combine the whole thing, and that's where the quadratic optimization comes in. Quadratic optimization is essentially you're minimizing a quadratic function subject to a bunch of linear inequalities and a bunch of equality conditions. And in order to solve this, you have to solve what is called as the Karsh-Tucker equations, KKT conditions, which is this set of equations over here. In our case, we actually don't need to deal with these inequalities. We just need to deal with these equality conditions, which means that it simplifies the solution to this quadratic problem significantly, because all the last two set of conditions don't exist. So all you're left with are equality conditions, which can be solved as a simple system of linear equations, which is exactly this. So in order to solve the equality constraint quadratic optimization problem, you just need to solve this system of equations. And if it is in this norm form, it's also called a factored form. You just have to take this L transpose L in order to get the solution. A are your equality constraints. Okay. So that's basically it. This is the quadratic optimization, and we're going to use this in order to connect our finite differences with our mesh tree methods and get the solution out of it. So how does the quadratic optimization framework work? You start with your domain, you get the boundary discretization associated with the domain. No need to mesh the interiors. You generate a background tensor grid, which is actually trivial. It's literally saying in X direction, I need 20 points, in Y direction, 20 points, get a tensor product grid of that, you're done. It's a one-liner. Once you have that, you need to get a PDE discretization on the tensor product grid. I gave you an example of how to do that using the finite difference function using NDSolve. So that L matrix can be generated very easily. Then next part is to generate the boundary constraint. And so you need to get these coefficients C, these weights, associated with the underlying tensor product grid function information at your boundary node. So XIB represents the nodes at the boundary. XJ represents the underlying tensor product grid, the locations of the tensor product grid. And so once you have this using mesh tree methods, you essentially end up with a system of linear equations, which is written as C dot U equal to H, where H is the boundary condition information that is given to us as part of the system of PDEs. Okay, once you have your L, you have your C. It's a simple case of then combining it into using the quadratic optimization method, wherein you're interested in minimizing the residual of your PDE, which is that LU minus F, subject to the boundary constraints, and that's it. So you can solve this. You could use the built-in function quadratic optimization in Mathematica, but this is literally, that's you're taking a bunch of extra steps. You can just, once you have the matrix L, the matrix C, the vector F, and the vector H, you just simply need to generate a matrix, a sparse matrix no less, and just solve that. Okay, so that's just the math of it. I want to quickly show you one example of how this whole thing comes together. So first we're going to do is we're going to define the domain. The domain looks like this. Note again, I want to emphasize there's only boundary information that we are going to consider. The example we're going to use is we're going to solve an elliptic PDE on it, wherein the analytic solution is already known, so that we can compare and do some error analysis. Okay, so we're going to first, I'm going to show you the visualize the exact solution. So this is what the exact solution looks like. It's a whole bunch of sines and cosines, but the important thing is the analytic solution is known, so that the elliptic PDE, the right-hand side of that, is also known analytically to us. So the first thing I'm going to do is I'm going to get the coordinate bounds of my mesh, of my domain, and generate a tensor product grid, which is this part. And from there, that's just generating the background mesh, which is this. Okay. So I have, and we're going to approximate the PDE in this background mesh. The way we do that is using the finite difference method. We're going to get the Laplacian. Remember, I'm solving the elliptic PDE here as an example. And so I end up generating this L transpose dot L, which becomes my Q matrix. And my right-hand side is the L dot B, which is the Q RHS. So I'm going to evaluate that. Then I'm going to generate the information associated with the boundary conditions. This RBF derivative is a built-in. It's not a built-in function. It's a function I've written. It's part of the utility functions that's available in this notebook. I'm going to the radial basic function I'm using is just r to the power 15. You can use your own, but what this RBF function does is it generates a whole bunch of compiled functions, so that you can get a lot of computations done quickly. Once you get that, I put it through another function called arbitrary grid differentiation matrix 2D. This is basically doing the generating the matrix that does a function approximation. The 0, 0 basically means that that's the derivative approximation. In this case, they're Dirichlet boundary conditions, which is why it's 0, 0. If it was a Neumann condition with or du dx, then it would have been 1, 0. If it was du dy, this would have been 0, 1, so on. And so we get our CMAT and CRHAs, which are our boundary information, and that also comes back in the form of a sparse matrix. And in this case, I have used 200 boundary nodes that are embedded in my background grid. So that's why your matrix will have a dimension of 200 by whatever is the size of my grid. In this case, it's a 41 by 41. So that's what it is. So now that I've generated that, we basically solve this and we get our solution X. Okay, and so this part, this matrix, is basically can be efficiently generated using their sparse block matrices. You don't need to combine them. You can combine them in any way you want. You can use join, but this is a very efficient way of doing it. You just use sparse array, sparse block matrix, and you get the final matrix. You get the RHS. In this case, I added a regularization. You really don't need to do this. I found that it sometimes improves the stability of the system, but for this case, you may or may not need it. And once you solve that, you get your discrete solution. You pull that out. You have your background grid. Send it off to the interpolating function. Let it do its thing, and you get back a result. That's pretty much it. And then you can visualize the result. It'll take just a few seconds because I'm generating a high resolution solution. And so the first plot you see is the computed. The second plot you see is the exact, and the error you see is the third plot. So it is a pretty good error. As a matter of fact, I'll show you in the coming slides that the error that you obtain follows exactly the same trend as you would expect from finite difference approximations. So if you were to double the grid size with a fourth order thing, your error goes down by a factor of 8. So you do retain all the error convergence advantages that exist with finite difference methods. So I just want to quickly, so this was, you just embedded one domain, all the boundaries inside this one domain. but the framework and the methodology is actually flexible enough that you can manipulate it to do a whole bunch of different things. For example, instead of one big domain, I can use two domains. I can use one domain which is marked in red, and a second domain which is marked in black. I can combine those two domains together and solve the PDE on that with the solution existing in domain 1 and domain 2. That's completely possible with this quadratic optimization framework. Let me show you the result associated with that. So in this case, I use two domains. One is a horizontal rectangular block and one is a vertical rectangular block. And here's the solution associated with it. Okay, so the first one is the solution with the horizontal block, and that's the error associated with it. The error bar didn't show up. Oh, it does. There's your error bar. It does a fantastic job with the second order with these two domains cases. And if you were to overlap the solution for both of them, this is the result you get. You add so because there is overlapping condition in this framework, you need to add some continuity conditions in this overlap region. And once you add this continuity condition as part of your equality constraints, you see that the solution in that overlap region matches quite well between the two regions. If you were to do an error analysis of this, you can see that it matches identically to what is predicted by finite difference methods. So you can use a second order method, third order method, fourth order method, go pseudospectral if you need to. It should be able to handle it because the background grid relies on finite difference methods. So you have the flexibility of going to higher order methods without loss of generality. So here's so I just showed you an example of the 2D case. You can go 5 regions and block it off. So and all you need to do is then consider the information associated with each one of the subdomains in the when one region overlaps with the other, you just need to enforce continuity conditions, which is basically saying, hey, these nodes are common. They exist between these nodes exist between region 1 and 2. Let's enforce a continuity condition in there, and that's about it. And you're able to get the solutions. Again, the same convergence property exists. I know I've run through this, but the math is basically just the same thing. You just have to add more and more constraints in there, but then that's pretty much it. So that basically the conclusion that I have is that you could use the quadratic optimization framework. It is a viable candidate to solve PDEs. I only showed you one example of an elliptic PDE, but you can go to all kinds of nonlinear PDE. You discretize it, and you should be able to use this method. If you have nonlinear methods, there is an entire books that have been written on how to solve nonlinear quadratic optimization problem. You can use that. Quadratic optimization also allows you to give it this methodology gives you a natural starting point to solving inequality constrained PDE problems associated in different fields. So if you have inequalities or you have other kind of constraints that are a part of the optimization framework, you could then use this methodology to address those problems. So that's what I have. I hope you found this informative. I know I ran through a lot of it. If you need more information, you can always get in touch with me. And yeah, I'll conclude at this time. And thank you for sticking around and listening to my talk. Appreciate it.
Thank you very much to all our presenters. This has been a great colloquium. On our way out, I'll just make a quick finite element methods joke, which is that we have a very high information density, very high resolution mesh of presenters that we have here. So of course, because we have such a high resolution mesh, we ran over our time constraint. So with that final thought, audience, thank you so much. There'll be an exit poll on your way out. Please do give us some feedback. And thanks again to our presenters, audience in the chats. Feel free to ask questions and give a round of applause to our presenters. There is also an opportunity in the exit poll to leave some more questions. So with great thanks to everyone involved, we'll leave it at that.
Thank you.
All right, thank you very much, John, for hosting this event. To our presenters for their magnificent talks, and of course, thank you to our kind audience. That's all we have for you today. But please stick around. As John mentioned, we have an after-event survey. I'm going to share that link with you right now. You will also be prompted to it when the webinar or this event ends, and we will share a recording email as soon as possible. Maybe you'll get it on Monday. With today's recording, it'll contain some other useful resources as well, so be sure to check it out. And with that, I'm going to say goodbye to you. Thanks again, everybody. It was our pleasure to have you here. Enjoy the rest of your day.